Hi and welcome to this 7th lecture in this course on reinforcement learning. My name is Hado van Hasselt and today I will be talking to you about function approximation in reinforcement learning. In terms of background material, chapters 9 and 10 from Sutton and Barto are highly recommended, and we'll cover some material that's captured in chapter 11 as well. And in terms of context, we are always considering this interaction loop, where there's an agent interacting with the environment by picking actions and observing the environment. And then reinforcement learning can be considered the science of learning how to make those decisions. How can this agent deal with this interaction stream and somehow pick actions that give it larger and larger rewards? The rewards, not depicted in the figure, could be inside the agent's head or they could be part of the observation, depending on how you want to model your problem. Inside the agent, in any case, there will be some sort of a policy that determines the actions. And in addition, the agent might have value functions or potentially models as well. The general problem involves taking into account time and consequences, because the action influences the immediate reward, but also potentially the agent's state and also potentially the environment state, which means that certain actions might have very long-term consequences. In addition, these consequences might not be immediately obvious. For instance, an action might change some internal state variable in the environment, and it might not be immediately observable what that means or what that matters, but it might influence later observations or rewards. Now in this lecture we're going to talk about function approximation, and first we're going to talk about why we need that. So first we're just simply pointing out in some sense that the policy, the value function, the model and the agent state update and all of these things that are inside the agent can be viewed as being functions. For instance, a policy maps the agent's state to an action or to a stochastic policy from which you then sample an action. A value function maps a state to a value, which is an estimate of the cumulative reward into the future. The agent state update itself maps the previous agent state and the observation into some new agent state. So these are all functions, and we want to learn these from experience. Why do we want to do that? Well, multiple reasons, one of which is flexibility. As we talked about in the very first lecture, I quoted a paragraph from a paper by Alan Turing there, where he argues that maybe it's easier to program something akin to the mind of a child than it is to program something akin to the mind of an adult. Because maybe it's actually easier and also maybe better, actually, more flexible, to write something that can learn from experience than try to list all of the rules you may have learned from experience. In addition, if there's too many states, we will need some sort of approximation. This is a separate point, because this is no longer just about learning, but this is really about function approximation, that this is important. And when we use neural networks to represent these functions, then this subfield is often called deep reinforcement learning these days. That term is actually relatively novel, it's like 7 to 8 years old, but the combination of reinforcement learning with neural networks is in some sense a quite natural one and is actually fairly old and has been suggested at least in the 70s already. So in this lecture, we'll concretely consider predictions, so value functions, including some value-based control, so using these predictions to come up with policies. In upcoming lectures, we'll talk more about off-policy learning, approximate dynamic programming, which is the term we use to refer to this more generic field of study, where we're not necessarily sampling, but we're just considering what if you have approximations in your dynamic programming algorithms. This could include sampling, this could include function approximation, but it could also be from other sources potentially. And this will allow us to talk about these updates in a theoretical sense and analyze what they are doing. This will also be in an upcoming lecture. We'll also talk about learning policies directly. So as I mentioned, the policy itself can be considered a function. So you could consider updating that function with policy gradients. We briefly talked about those in lecture 2. We'll come back to that in a later lecture. And we'll talk about model-based RL as well. In this lecture, we're focusing on predictions because it's nice to be able to focus on something when we talk about this function approximation, but a lot of the insights, they do transfer to these other cases as well, as we will see. And in terms of motivation, well, why do we want to do that? Because we're ambitious. We want to solve real problems. We want to solve large problems. And actually, even small problems are large problems, because the game of backgammon, one could argue, is not particularly large compared to the real world. It's just a game. But turns out backgammon already has 10 to the 20th different possible states. So if you would try to enumerate all of those in a large table in memory, you quickly run out of space if you try to do that for these type of problems. Because if we then go to a different game, like the game of Go, we notice that this actually already has 10 to the 170 states. That's an enormous number. You can't feasibly store that in memory in a computer and then try to learn a value function for each of these separate states. Actually, it can even get worse because, for instance, let's consider helicopter flying, in which the state spaces could arguably be taken to be continuous. So you could view the state space could, for instance, be the position of the helicopter in space. So there's this three-dimensional space location. But in addition, maybe there's other inputs as well, like there might be a wind sensor that tells you from which direction the wind is blowing and how fast it is blowing. And these inputs could all be real valued numbers, which means that the state space is inherently continuous, which means that if you would like to enumerate them, there's infinitely many states. And of course, maybe as the ultimate example, you could think of a robot in the real world where the environment is actually equally big as the real world is. And in that case, it's obviously impossible to enumerate all of the states because any computer that would have to do that would have to live in the real world and hence should be necessarily much, much smaller than the world is. So this is a common thing that we have in mind when we think about reinforcement learning. We want algorithms that can be applied to this setting where this environment is just humongously large and the agent must be necessarily a lot smaller. So the mind of the agent, including its memory capacity, must be necessarily smaller than the environment. There are, of course, small problems, smallish problems, in which you could still enumerate all of the states. And in that case, maybe you could try just doing tabular approaches. But in general, we want these algorithms to also apply to these larger problems. So this is our motivation for why we want to consider function approximation. And the intent is, of course, to apply the methods that we've already been talking about for prediction and for control. So let's talk a little bit about value function approximation now. So far, we've mostly considered lookup tables, although I've already mentioned linear function approximation and other things in earlier lectures. But in the tabular case, each state has a separate entry and we just update that, or each state action pair has a separate entry. But the problems with that is that there are too many states, as I mentioned before, so you cannot fit them in memory. That turns out it's not the only problem. A different problem is also too slow to learn the value of each state individually. So think of it this way. So if you have a problem that is not too large, let's say there's 1 million different states. We can store 1 million numbers in modern computers. That's not a problem at all. But then still, if we would update each of these state values individually and separately, then it would take quite a bit of experience to learn reasonable value estimates for each of these states. And indeed, this feels inefficient if these states have some commonalities, which we would then completely be ignoring. So if these states can instead be viewed as being similar to each other, then maybe you would expect, or maybe you would want, the value of a certain state to be updated when the value of a very similar state is updated. This is called generalization. In addition to those 2 points, individual environment states are often not fully observable. So the environment might not just be big, it might also not be fully observable from your observation stream. So we need to somehow infer what's going on in some sense, or at least up to the point where we can make meaningful predictions or pick meaningful actions. So our solution for all of these problems essentially will be to introduce function approximation. For now, we're just considering the predictions. As mentioned at the beginning, we're going to consider value prediction in this lecture. And what that means is we're going to introduce some parameter vector w as before, where now the value function is parameterized with this w. It's a function of state somehow, where the state is the agent state, and we're either approximating the value of a certain policy or maybe of the optimal value function. The algorithms we'll get to in a moment, but the idea is that we're going to approximate these and then update the parameter. For instance, using Monte Carlo algorithms or TD learning or any other similar algorithm that you might want to use. And then hopefully, if we pick our function class correctly, and we'll talk about that more, we will be able to generalize to unseen states. So in any case, if you have such a function, the values of these unseen states will be well defined. You could of course also have this for a table. You could just, if you know all the states that you could possibly end up in, you could at least initialize the values to be, for instance, 0 arbitrarily. But if you just have a function class that automatically maps every possible inputs to a valid output, then you automatically have this mapping and you have a valid state estimate for every state. In addition, I just want to briefly talk about the agent states, but I'll actually not go into a lot of depth in this lecture. I'm just going to mention it because it's already very important, but we'll get back to that in a subsequent lecture. So I mentioned that one of the problems might be that the environment state is not fully observable. So essentially the environment state is not equal to the observation. Then, as always, we're going to rely actually on the agent state instead. And we're going to consider the agent state update function here briefly, which we could also consider to be a parametric function of its inputs, which are the previous agent state, the action, and the observation. and potentially the reward as well, if that's not part of the observation. And it has some parameters here denoted omega. Now, we already discussed you could pick this to be something. You could pick this just to be, for instance, the observation, the agent state, at which point the omega is maybe not relevant. Maybe there are no parameters for that function. But maybe in general, that's not very particularly useful, right? If you look at just the observation, you might not see everything that you need to see. So this agent state, which we here denote with a vector notation, but we will continue to use the random variable notation as well, should contain everything that's useful for you to make value predictions or to pick your policy. And that means that the agent update function is actually quite important and might need to capture things like memory, for instance. It might be that you have to remember what you've seen before. We talked about an example in the first lecture where maybe a robot has a camera, can only look in front of itself, can't see what's behind it, but maybe it needs to remember what is behind it to pick suitable actions. This would be captured in the agent state, and maybe we should think about learning that. In this lecture, we won't go into that, but I just wanted to remark it. Also to be clear that in the subsequent slides, whenever I have a state, it's always going to be the agent state. And this is basically just going to be some vector, or the observation. Okay, now we're going to talk about a couple of different function classes in some a little bit more detail, just to talk about the differences between them. So we started by talking about the tabular case, right, where we just have a table. So our function class here is tabular. And then one step up from that would be state aggregation. So in a table, we have an entry for every single state. For instance, let's consider for simplicity that it's fully observable. So you literally observe the environment state and you just have an entry for every environment state. In state aggregation, you would instead have an entry that merges the values of a couple of states. So basically, we just partition the state space into some discrete small set, potentially, so that we can maybe learn the values of these partitions instead of learning them for every individual state. And then indeed, we would get some generalization because all of the states in the same partition would then be updated with the same algorithm and hence would obtain the same value. So if you reach a new state in a certain partition that you haven't seen before, then it would automatically already have a value and it might be a suitable value. Now, one step up from this will be linear function approximation, and I want to, for now, consider a fixed agent state update function, and then a fixed feature map on top of that. So this is why things will be linear, because we're going to assume that the agent state update function, for instance, it could just pick the observation or do some other fixed function there, doesn't have any parameters. The feature map doesn't have any parameters, and instead, all that we're going to learn are the parameters of the value function, which uses those features as input. So there is still an agent update function. It might be a simple one, but we're just going to ignore that in terms of the learning process. Now note that state aggregation and tabular are actually special cases of this more general class, because in the tabular case, we could just consider the feature vector to have as many entries as there are states, and then have the entry of the current states would be 1 whenever you're in that state, and all of the other entries would be 0. So it's a one-hot representation, as they sometimes call this, where the state is kind of picked out by the feature vector. Now, state aggregation is very similar, except that the size of the feature map is no longer necessarily the same size as the number of states. So n, what we call that here on the slide, the number of outputs of this feature mapping, so the number of features in your feature mapping, would not be equal to the number of states, would typically be much, much smaller. And you could indeed even apply this to continuous state spaces. But then it would still be a one-hot representation when we do state aggregation. So there's some mapping that says, oh, if you're in this state, then this entry must be 1 and everything else must be 0. And if you're in similar states, maybe the same entry will be 1 and everything else will be 0. But if you're in a different state, then a different further away, for instance, right, then a different entry would be 1. So it's still a one-hot representation, but it's a smaller feature vector than if you would do the fully tabular approach. And both of those are special cases. You don't need to have a one-hot feature representation. You could consider much richer function classes here. Now, one step up from that, if we're going to be even more flexible, would be to consider differentiable function approximation. In this case, our value function will be a differentiable function of our parameters w, and it could be nonlinear. For instance, it could be a convolutional neural network that takes pixels as input. You don't need to know right now what a convolutional neural network is. If you don't know what that is, it's just some nonlinear function. And one way to interpret this is that you can consider the feature mapping now no longer to be fixed. So we take whatever the agent state is as input, and for instance, the input could just be the observations, could be the pixels on the screen when we're, say, playing an Atari game or something like that. And then instead of having a fixed feature mapping, you could consider this to be a learned feature mapping, where something maps it into features, and then there's an additional parameter on top of that that maps it into values. In the notation, we're going to merge all of those features into one big vector W, but it won't be a linear function. It will be some nonlinear function where these parameters are used in different ways. So what we're requiring here, why we call this differentiable function approximation, is that we can still compute a gradient because we're going to consider gradient-based algorithms. That's not a strict requirement, but it is one that we're going to use here, and it allows for very rich function classes such as deep neural networks. Okay, in principle, any of these can be used. But it's good to acknowledge that reinforcement learning does have certain specific properties, or maybe often has certain specific properties, which might interact with the function class. So it's good to be aware of those. The first one that I'm going to mention is that the experience is not identical and independently distributed, with which I mean that if you're going to learn online from a stream of experiences just coming at you, then successive time steps are actually correlated. This is not necessarily a problem. I'm not saying it because it's necessarily a problem, but I'm saying it because it's slightly different from the case in which many of these functions have been developed. For instance, deep neural networks were originally often developed and tuned in cases of classification. For instance, MNIST, the digit classification. And then some choices that were made there might not be completely appropriate for reinforcement learning because we're breaking some of the assumptions, such as that we can sample each of these learning examples independently. In addition to this, the agent's policy affects the data it receives. What I mean with this is that reinforcement learning is an active problem, and this has multiple consequences, including that actually one benefit of this is that you can maybe actively sample data in a way that is useful for learning your function. You could literally have an exploration technique that maybe seeks out certain parts of the state space in order to improve your value estimate specifically over there. You can't actually, it's not active learning, you can't just sample any sample that would be within the field of active learning. That's the typical assumption, that you have a database and you want to indeed actively pick which samples, but you can pick from all of them. That's not typically the case in reinforcement learning because the way we're interacting with the world. So if you want to sample a certain situation, you actually first have to go there. But it is an active process, and that's interesting. But it also causes some issues. For instance, the regression targets are often non-stationary. This is, for instance, because we're doing control. Like, we might be changing our policies as we go. And this might not just change the targets for our regression, our value targets, for instance, if we bootstrap, but it might also change the data. So it's actually non-stationary in more than one way. In addition, like I said, the bootstrapping is important. So even if the policy is fixed, so even if your policy is not changing, the targets might change because your value estimates that you're using to construct your targets could be changing. So in TD, we're using our value estimates, and those initially are not very good, but later they might become more accurate. In addition to this, the world itself might be non-stationary. For instance, there might be other learning agents in the world, and maybe we will also want to deal with those cases. And similarly, but differently, the world might just be very, very large. So this might mean that you're never actually quite in the same state. And these last 2 points are actually quite closely related, because if we allow for the world to be partially observable, then if the world is sufficiently large, it might appear non-stationary to you. Because you might think, oh, I'm going to that room, I'm going somewhere else, I'm going back to that room. Things have slightly changed. Maybe the sun is now setting where it wasn't setting before. Or maybe all of a sudden there's a different agent in the same room. And this is not maybe literally non-stationary. Maybe the actual underlying, say, physics of the world are not changing, but you don't know all the latent variables that are in the environment state that make these things change. So in some sense, non-stationary and very large are in some sense similar, but of course they have different connotations. You could have a very tiny non-stationary problem as well. So which function approximation should you choose? We covered a couple of function classes. Well, it kind of depends on your goals. And one distinction to make is that for instance, the tabular case, we have really good theory. We understand these algorithms really well. We know when they converge, we know where they converge, they're quite stable. The assumptions for convergence are not very strict, so you can fairly easily apply them and be pretty certain that they will learn something. In addition, I didn't put this on the slide, but they actually also tend to learn relatively well and fast if the state space is small enough. But they don't generalize, they don't scale. You can't apply them to very large problems as discussed. Now in the linear case, we're already a little bit more flexible on our function class. We still have reasonable good theory, so we understand these methods quite well. We know when they converge and where they converge in many cases. But of course, we are dependent on this fixed feature mapping. So we do require very good features. Now, this is a bit of a subtle point because the people are still debating this in some sense, because there's multiple aspects to this. One is that, of course, you're going to be limited by the features that you have. And maybe that would be a good reason to learn these features. Most people these days are in that camp. But you could also argue that maybe it's okay to have somewhat poor features as long as you have sufficient of them. So the other alternative would be to have linear function approximation, but with a very, very rich set of features. And then maybe you still have a good enough set of features that you can pick out the ones that you really can use in the context that you require them. And then, of course, there's nonlinear function approximation, which is less well understood, but it scales really well and it tends to work quite well in practice until it doesn't. And then sometimes we don't really understand what's going on in some edge cases. But of course, our experience with this and our understanding of this has been growing quite a lot over the recent years. And it's really flexible. And importantly, it's much less reliant on picking good features by hand. And I personally find this to be a very convincing point and a very good point. Because one thing that this means is that you can apply these methods to problems that you don't really understand that well. But as long as you have a well-formulated reward function that you are certain is the right reward function, you could apply these reinforcement learning methods and then still get better, find good policies for these domains without really needing to understand what appropriate features would be. And in fact, we see more often these days over and over, not just in reinforcement learning, but also in deep learning and related fields. When applied, these algorithms that don't try to hand engineer features, but instead try to learn them from data, tend to outperform methods in which these features are hand engineered. So that's interesting, and it relates, again, back to that point that Alan Turing was also trying to make. So deep neural networks are typically used in this last category of nonlinear function approximations. And in some sense, depending on how you define these things, some people would argue that maybe any nonlinear function could be argued is in some sense some sort of a neural network. It might be a weird one, a very strangely structured one, but in some sense these are somewhat similar. So sometimes neural networks are used almost synonymously with nonlinear function approximation, and these tend to perform very, very well in practice and therefore remain a very popular choice. And there's also lots of research, of course, happening trying to understand these methods better. Okay, now this brings us to our next topic, where we're going to talk about gradient-based algorithms first a little bit in general. So we're going to talk a little bit, just a very brief primer on gradient descent and stochastic gradient descent. And we're going to talk about this because of course we're going to use that for value learning in a moment. So for now, let's consider some arbitrary function j. This is just some function only of the parameters, right? There's no state input, there's just parameters as input. And we're going to consider its gradients. Just as a reminder, a gradient is a vector and it contains as its elements each of the partial derivatives for this function j with respect to that one parameter out of w. So j here is a scalar function, with which I mean that the parameter vector can be large, but the output is just a number. And we're considering the gradient of that function j with respect to the parameters, which we of course should evaluate at certain parameters, right? The gradient depends on where w is at this moment. And the goal could then be to minimize j. So one way to do that is to move our parameters w in the direction of the negative gradient. And one way to do that would be the algorithm on the slide. There's actually different ways to do that as well, that are similar but slightly different in, for instance, how they pick the step size or exactly how they move or the direction they move. But a lot of the algorithms derive essentially from this main algorithm, which is the gradient descent algorithm, where we have some step size parameter and we just move slightly in the direction of the negative gradient. The 1/2 here is optional. Maybe I should get rid of that. This is kind of assuming that there's a square lost, that j is some sort of a square, and that therefore the 1/2 will cancel out with that. So the step size parameter should be in some sense small, because then if we take a small enough step, we're in some sense certain that we're going to decay as long as this function j is smooth enough. So what I mean with smooth is that the function can't have a very big discontinuity. So if you know your function is somewhat smooth, then you know if your step is small enough that the gradient will have pointed in the right direction, and indeed it will go down. Now, of course, in practice, there's a bit of a trade-off happening here because you don't want to make alpha too small because then learning is very small. So instead, you typically tune this to get good performance. Now, if we plug in value functions, so here we have the squared loss that I promised. For instance, we could consider this one where we are simply interested in this one number, right? Again, j doesn't take state as input. It's just a number that depends on your parameters w. And the way it depends on that here, we define that to be the expectation over some distribution of states, for instance, due to your policy and of course the MDP dynamics. And we want to consider the square difference between the actual true value of your policy, so we're doing prediction in this slide, and our current estimate. And that's something that we might want to minimize, right? This will be a predictive loss. And then we can just consider this gradient descent algorithm. Here the 1/2 comes in handy because it cancels out with the 2 that comes from taking the derivative of the square. We note that the distribution in this case does not actually depend on our parameters, so we can just push this gradient into the expectation, and then we get this algorithm, this update, if you will, where the update to the weights, delta w, would be small step size alpha times the expectation under that distribution over states of the target, which is our true value function for that state, minus our current prediction times the gradient of that current prediction. This is an expectation, so we can't actually typically use that unless we really have that distribution over states. But if we want to use this in practice, we can sample this, and that means that we're going to sample the state we're in, and we're also going to sample this true value of the policy. And one way to do that would be to plug in the Monte Carlo return, which is indeed an unbiased estimate for the true value of the policy. So this update, this stochastic gradient descent update on the slide here, is an unbiased estimate of the gradient descent algorithm one line above it. And that means that if we take our step size to be small enough and we take enough of these steps, that we will, on average, move in the direction of the gradients, and we will also reach the same, basically, conclusions. We reach the same solutions as the full gradient algorithm would. So in that sense, stochastic gradient descent is fine, and it's just another reason to pick a small step size. So not just because then the gradient is valid, but now also to average out the noise in our estimate of the gradient. So we're often a little bit sloppy with notation. This is just kind of a warning for that. So whenever we drop terms, so let's say we, for instance, write the gradient of v and we don't have w's anywhere, and we don't specify where we're taking this, then typically we mean, when we have a gradient, we mean with respect to the parameters. So we have gradient of v just means with whatever the parameters of v are. So if those are w, then this would mean the gradient with respect to w. And then we're also typically taking that at whatever the current value of these parameters are. So this is something that you'd actually have to be explicit about. The gradient itself outputs in some sense a function, and you still don't have to plug in the parameters where you're evaluating that gradient. And this is typically done in notation with this bar where the subscript tells you where we're evaluating the gradient. But people are often very sloppy with the notation in this, and there's lots of shorthand. For instance, people might write instead the gradient with respect to wt of the value function of wt, instead of having this bar notation. And that's fine as long as from context it's clear what we're talking about. So I just wanted to highlight that here so that you have a feel for, oh, if there's something that gets dropped from a notation, how should we interpret it? It should be clear from context. Okay, and now we're going to go and talk a little bit more in depth about linear function approximation, which is going to be useful to understand the algorithms and also some of the limitations of the algorithms. So we talked about this previously, but I'm just going to reiterate a couple of things that we said before. We're going to represent the state by some feature vector, where this this feature mapping x is going to be considered fixed. So we have n elements here, n different features. These are just numbers, and they're functions of state. And it might, for instance, take the observations as input, or more generally your agent state, and outputs some feature vector of a certain size. And we also introduce some shorthand where if we apply this function to state at st, so at time t, we can also just write xt. And we can kind of pretend that these are just our observations as far as the algorithm is concerned. The algorithm only gets access to xt. It doesn't actually get access to st anymore. It just gets access to these features instead. So, for example, these features could include distance of a robot from some landmarks, or it could be trends in the stock market, or it could be piece and pawn configurations in chess, or whatever you can come up with which might be useful for the problem that you're trying to solve. And I'll also show you an example where you can somehow find ways to kind of automatically pick reasonable features for some problems. So this is that example. This is called coarse coding, and it's one way to come up with a feature vector. It's a little bit related to that state aggregation that we talked about before. But in this case, we're not going to actually subdivide the space into disjoint chunks. So what you see here in the picture is that we've actually subdivided a two-dimensional space. For instance, you could think of this as a location if you want to make it concrete. I didn't make it very concrete here. And we're going to subdivide this space, but into overlapping regions. And then whenever we're in such a region, so we're here at this X, say, and then we're going to have a feature that is associated with each of these circles. When you're in the circle, the feature will be 1, and whenever you're outside of the circle, it might be 0. If you do that with this representation, in this case, 3 features will be equal to 1, and all the other features will be equal to 0. So this is no longer a one-hot representation, as we discussed for the state aggregation or the tabular cases. In this case, it will be a few-shot representation in some sense. The features are still binary, they are either 0 or they're 1. But it's in some sense already a richer representation, because as we can see here from the figure, if you get these 3 regions in some sense to light up, we actually know we must be in the intersection of all 3 of them. And that can be useful information. But in addition to that, we will still have some generalization. If we're going to update the value associated with a state in this very darkest region over here, that means that a different state, say at y, will actually also be updated a little bit, because it shares one of the features with this state that is going to be updated. So if we think of the linear function that is going to be applied to this, it'll have a weight associated with each of the features. So if we change the weight of that feature, that means that any position that shares that feature, where that feature is 1, will also experience a slight change in its value. Now, I described the binary case for simplicity, where you're either in a region or you're out, and your associated feature is either 1 or 0. But of course, that's not the only option. You could instead also do something like over here, where you have some sort of a distance function that might be, for instance, Gaussian. And instead of saying you're in a circle or you're out, we instead have a bunch of center points of these circles, and we just measure how far you are from each and every one of them. Which means that in this case, for instance, we might have this feature light up a little bit. Well, actually quite a bit, because we're a little bit closer to its center. And this one light up a little bit less, because we're farther away from its center. Maybe even the feature over here still lights up very lightly, but very much less so than the features much closer. Now, of course, you would have to, similar with the circles, you would have to consider how far do you want your feature to be sensitive. But it would provide a way to be a little bit more continuous with your value functions. Whatever you do there, basically the idea is then you have your representation and you expand this into a bunch of different features, and then you compress that with your weights, which are here denoted theta. But you can think of this as being the same as the w from the previous slide, into a single number. Why do we say expand here? Well, in this case, note that we had a two-dimensional representation. We could have also maybe had say an xy location, which would constitute two numbers, and we could have fed that to the agent. But maybe it's really hard for the agent to turn those 2 numbers with a linear function into a valid value estimate, right? The only thing you can do then is some sort of a linear function over the state space. You can't have any nonlinearity in terms of your location and how the value reacts to your location if you would only feed in the actual location numbers, the xy coordinates. So what we're doing here instead is we're turning those 2 numbers of this 2-dimensional space into very many numbers, as many as we've defined these circles. So in some sense, we're actually blowing up the representation in order to then be able to apply a linear function to that. This is a common technique. It's also used in, for instance, support vector machines. Doesn't matter if you don't know what those are, but if you do, then you might recognize this principle, where we're basically just blowing up the feature space into something large in the hope that then the feature representation will be rich enough that a linear function suffices. That if you then apply a linear function to these features, you still have a good enough approximation. Now, it might immediately be obvious that there are some limitations to this approach, or if not, then maybe let me point at some. For instance, it might be quite hard, so if you only have 2 dimensions, maybe you can define these circles and you're good to go. But what if you have many dimensions? What if you have 10 dimensions, or maybe even 100 dimensions? And this is not very fictional, because of course if we think of locations in the world, maybe we'll think like 2 dimensions, 3 dimensions, maybe that's enough. But as I mentioned for the helicopter example, a helicopter might not just be in a location in 3-dimensional space, but it might also have other sensors. It might have some audio sensors, it might have wind sensors, it might have other sorts of sensors. It might be measuring, I don't know, air pressure or humidity. So these would all be dimensions, and it might actually be very hard to somehow figure out a good subdivision of that space without making the feature representations extremely large. This is sometimes called the curse of dimensionality, which is actually a term due to Richard Bellman, also known from the Bellman equations. Okay, so this is just meant to be an example of how you could somewhat automatically construct these features, because you could imagine if you do have a fairly small dimensional space, like 2 dimensions, then you could just sprinkle a couple of these circles in there, and you maybe don't have to think very carefully about where they are. Maybe you don't need to understand the domain that well for you to get a reasonable a reasonable feature representation. But of course, there is a choice here, and here's a couple of examples. So on the left-hand side in A, we see narrow generalization. We've picked these circles to be fairly small. And what this does is it allows you to be quite specific. So if the value function is updated only in this region that lights up, and then maybe mostly updated in the smallest region because of your representation, that means that you have narrow generalization. If you update this state, states fairly near to it get updated as well, but states further along are not. And that's both good and bad. This is a double-edged sword. If you have narrow generalization, this means the narrower it becomes, the more specific your value function can be, and the more precise it can be. If you need very high resolution in some sense in your value function, because the actual value function might, for instance, be quite bumpy or weird, then it might be useful to have very narrow generalization. But it does mean that learning might progress quite slowly, because there's very little leaking from the state information from states farther away. So instead, you could consider having broad generalization, where the overlap is much larger, the circles are much larger. Then updating just the state in the middle would actually update a fairly large region of your state space. And this can be useful, because it might speed up learning, but you lose out in terms of your resolution at the limit. When you've learned your value function, there's a limit to how precise you can make it at every situation. Of course, depending on your dimensions here, we don't know what x and y are here in terms of dimensions. It could be that you actually want to pick something more custom, that the best representation would be asymmetric. So this already alludes to the fact that it can be quite tricky to pick these things in general. The other thing I want to note is that we're actually aggregating multiple states, and this means that the resulting feature vector, and hence what the agent observes in some sense, will be non-Markovian. What I mean with that is that if you're in this little region here in the middle, and let's say the agent moves right, but it only moves a little bit, then you would end up in the same region, the same features would light up. So from time step to time step, while you remain in this small little region in the middle, the feature representation would not change while you're moving within that region. And then at some point, you actually step out of the region into the next one. Now this is why that's non-Markovian, because the time step at which that happens, as far as the agent is concerned, it can't tell, right? So there's actually some probability distribution happening here, where the underlying state, of course, there is a certain moment which you actually transition. Let's say the effect of the actions are deterministic. So when you move right, you actually move right. So maybe there's a true transition which is completely deterministic, but the agent doesn't know when it happens. So what happens here instead is that as far as the agent is concerned, at some random point in time, you'll transition from one region to the other. This is the common case, this non-Markovian is the common case when using function approximation. It's not specific to this, it's just very easy to visualize in this representation. But whenever you use function approximation, including deep neural networks and so on, you should count on the fact that in some sense, as far as the algorithm is concerned, there might be some partial observability. Because the function approximation will, if it's a good function approximation, it will in some sense generalize things. So for the linear case specifically, we do want to consider when good solutions even exist. So it's good to kind of do this mental check. So if you're given a certain feature representation, or if you're considering a certain feature representation, if you're picking it yourself, it's good to imagine Well, if I would have the best possible weights, what would it look like? Is it good enough? Is my generalization, say, narrow enough that I can have good enough resolution? Or is it broad enough that I can have fast enough learning? So it's good to just think that through for your feature representation, and then sometimes you might catch things. So, oh, there's no way the agent could learn this value function because it simply cannot be distinguished between these two different important states, for instance. Neural networks tend to be much more flexible in that sense. So if you just give pixels to the neural network, it could itself figure out how to maybe subdivide the space in some sense, right? And come up with some sort of an internal feature mapping that is maybe more suitable to the actual problem that you're trying to solve. Because you could imagine that if you want to make these feature mappings flexible, if you could make them flexible, that this could be a lot stronger, where maybe you have asymmetric generalization in some part of the state space, broader generalization in another part, and very narrow generalization in some part where it's really important to get the values right. A neural network can, in some sense, automatically find that. Okay, now we're going to move on to linear model-free prediction. So we're going to talk about how to approximate the value function with a linear function approximation. We talked about this before, but just to be very explicit, we're going to approximate the value function by having this parameter vector w multiply with this feature vector x, which we can write out very explicitly by just having a summation over all of the components of both of these vectors. That's just a dot product. And then we could define our objective to be, as before, a quadratic objective where we compare to the true value, v pi. For now, let's just assume that we have that true value, and we'll plug in real algorithms in a moment. But for now, we just consider that we have those regression targets, and there's going to be some distribution over states. This distribution is called D here, and for instance, it could be due to your policy, or maybe you have some different way to sample the states. Then this algorithm can converge to the global optimum if we do stochastic gradient descent, if we would regress towards this true value function, even if we use a stochastic update, where the stochasticity here comes from picking the value function. So you see the update here, and the update rule in this case is somewhat simple because in the linear case, the gradient of our value function will simply be our feature vector. So that means that our update to the weights, our stochastic gradient descent update, will be step size times prediction error, the true value minus our current prediction, where the true value is v pi and our current prediction is vw, times the feature vector. The feature vector here is just the gradient of your value function. In the linear case, those are the same. Now we can't obviously update towards the true value function if we don't have that yet. So instead we're going to substitute a target. This is similar to what we talked about before when we talked about prediction. And for instance, for Monte Carlo, we could plug in the Monte Carlo return. But of course, we could also do temporal difference learning. And then we could plug in the temporal difference target, which is just, in the one-step case, is just the immediate reward plus the discounted value at the next state. So this is now a placeholder for the true value of this state, and we can use that to have data-dependent updates, where we don't have any hidden information anymore. We don't have any privileged information about the true value of a state. Of course, we can also go in between these with TD lambda, as discussed before, where G lambda is a lambda return, which bootstraps a little bit on every step and continues a little bit on every step. And then this lambda trades off between these two algorithms, TD and Monte Carlo. As mentioned earlier, we're not going to go into that now, but in an earlier lecture, we then turned this into eligibility traces, where we could still have a causal algorithm that every step can update, rather than having to wait all the way until the end of the episode. So this is just a reminder that TD lambda can be implemented to not have to wait all the way until the end of the episode. And in fact, so can Monte Carlo. Now the return is an unbiased sample of the true value. And therefore we can kind of view this as supervised learning, where we just have a data set of states and returns. And then the linear Monte Carlo policy evaluation algorithm, which uses that return, but then instead of the gradient has this feature vector, will converge to the global optima. This is known because we're basically trying to find the minimum of a quadratic function, which is convex, and then stochastic gradient descent with an appropriately decaying step size will find the optimal solution. So that's nice under some mild assumptions. One of the assumptions is that we sample IID, but it turns out we can relax that assumption and it will also find the right solution if you don't sample fully IID, as long again as your step size decays sufficiently. And of course there's some other conditions as well. Just to mention one of those, You can only find a global solution, of course, if your data supports that. So one thing that you need, for instance, is that you can never make an irreversible decision, right? If there's just one state where you make a decision and you can never go back, that means that the information before going into that state won't have been visited infinitely often, which means that convergence then for those states at least is off the table. This is an assumption that's often called ergodicity. There's similar other named assumptions as well, but it basically means that your MDP is connected in the sense that you can always eventually at least return to states you visited before. So this actually converges also when using nonlinear value function approximation, although then it can converge to a local optimum. What we mean here is that if you have a nonlinear value function, your loss landscape might have multiple hills and valleys. Stochastic gradient descent on that loss landscape is still guaranteed to go down, but it's a local algorithm, so it could go down into some valley, get stuck there even though there's a lower valley, so a way to have lower loss somewhere else. But it's still nice to have that convergence, because it turns out we can't always guarantee convergence, and sometimes you might have parameters that diverge, that go to infinity, for instance. We'll see an example of that later in this lecture. So, of course, we can also consider TD learning. We know that the target here is a biased sample of the true value, but we can apply the same trick where we consider this to kind of be training data, where we have states and we have the associated targets for those states, and we could update towards those in a very similar way. So this is very similar to Monte Carlo. This is basically just doing a regression in some sense, but using the TD error rather than the Monte Carlo error. So this now is akin to a non-stationary regression problem, because we're using the value function itself to construct the target. So that's good to note that there's something that is different here from the Monte Carlo case. And the target depends specifically on our parameters. So it's not just any non-stationary regression problem. It's one where we're actually updating the parameters ourselves, and that makes the targets non-stationary. And that's something to keep in mind, because this turns out to be important for the stability of these algorithms. So now we're going to very briefly touch upon control with value function approximation. This will be relatively straightforward because we've talked about these things before. So just as a recap, we're going to do some version of policy iteration in some sense, and policy iteration depends on two steps. One is policy evaluation and the other one is policy improvement. To start with the latter, for policy improvement we could consider something fairly simple. So if we estimate action value functions, we can just use epsilon greedy policy improvement or greedy policy improvement, but then you wouldn't explore sufficiently. But we can just consider something fairly simple there, but then the approximation step is the difficult one if your state space is really large, and therefore we're going to plug in value function approximation for that step. So we're basically just going to approximate the value function for the state action pairs in a very similar way as before. And if we use a linear function, we could, for instance, define our feature vectors now as dependent not just on state, but also on action. And then they have this shared parameter vector W, which is applied to this feature vector and then gives you the suitable value estimate. The update is, as before, this is extremely similar to what we had before, except that everything now depends on states and actions rather than just states. And in the linear case, it turns out there's actually multiple things we could be doing. So a different way to approximate the action value function is as follows, where instead of defining a feature vector that depends on state and action, we could have a feature vector that only depends on state. Now, the action value function is now no longer a scalar function, which is why I bolded it here. So this is a difference between the previous slide. Let me go back to the previous slide first. Here we were doing the same thing as we were doing for value functions for state value functions, where we now have a feature vector that depends on both state and action. And then the Q value is just a number, right? So we have our feature vector X, which is the same size as our parameters W, and the inner product will just give you a number. Now we're going to do something different, where now we have a feature matrix W, and we're going to multiply a feature vector that only depends on state with this feature matrix. And the feature matrix is shaped in such a way that the output of this will have the same number of elements as we have actions. A different way to write down the same thing would be as follows, where we still have this scalar function for state and action, and it's going to be defined as indexing this vector that we get from this first operation with the action. So we have a matrix that has size number of actions by number of features, So when we multiply that with the number of features, we get a vector of size number of actions. And then we just index in there to get the action value for this action that we're interested in. This can also be written as follows, where we basically have a separate parameter function out per action, but we have a shared feature vector. So let me again go back. Previously, we had one shared parameter for all actions, and we had separate features for each action. Now we have one shared feature vector and separate weights per action. This is a slight difference, but it might be important in some cases. The updates are very similar to before. So we can just update the parameters now associated with just the action that we're interested in, and we can just not update the parameters of all the actions that we are not interested in because they correspond to different actions. So B here is just any action that's different from the one that we're updating A. And equivalently, we can write this down as follows, where I here is an indicator vector that indicates the action. So it's a one-hot vector that has as many elements as there are actions. And then only the element corresponding to the action that we've just selected has a value of 1, and all of the other elements has a value of 0. And then we take the outer product with the state features, and this will give us the update to our parameters. Now this might look a little bit complicated. Feel free to step through all of this fairly much slower than I'm doing right now. But I also, before you do that, it might be good to recognize that actually a lot of these things can be automated. There's a lot of software packages these days that use auto differentiation that allow you to basically compute derivatives without doing them by hand. So I want to make you aware of the differences between these methods, because they are different, these different ways to represent an action value function. But then in terms of computing these updates, we don't actually have to manually compute these outer products, for instance, by hand. Instead, we can just call a gradient function from an auto differentiation package and use that. Examples of those include TensorFlow, PyTorch, and I like JAX these days to do that. Okay, so this raises a question. Should we use action in, where the action is part of your feature representation, or action out, where we just have a state-dependent feature representation and then just compute all of the action values for all of the different actions? So the action in approach is when your feature vector depends on state and action, you have this shared weight vector, W. The action out approach is when you have a weight matrix, W, and you have features that only depend on state. One reuses the same weights across actions, the other one reuses the same features across actions. It's unclear which one's better in general, but they do have some certain other properties. For instance, if we have continuous actions, it does seem easier to have an action in approach, because you can't have an infinitely large matrix. So the action out approach seems much more troublesome if you have continuous actions. A different way you could deal with that is to parameterize your policy differently, not have literally a separate value for every action. If you have infinite actions, that might be hard. You can do that by having an action in network, or there are other ways you could do that if you want to do something similar to an action out network, but we won't go into that here. I just wanted to be aware of these choices, essentially, which are in some sense representation choices now. We're picking our function class in a sense, and even if we restrict ourselves to a linear function class, it turns out there's already design decisions that you have to make, and these might matter for the performance of these algorithms. For small discrete action spaces, the most common approach these days is action out. So for instance, the DQN algorithm, which I'll come back to at the end of this lecture, that was used to play these Atari games, did this approach where there was a neural network, a convnet in this case, which would take the pixels as input, then go through a couple of layers of convolutions and then a couple of fully connected layers. If you don't know what those terms mean, that's okay. But then in the end, it would output a vector with the same number of elements as there are actions. In Atari, there is up to 18 different actions, so this is a fairly manageable size. So it would just output a vector of size 18, and the semantics of this vector would be that for each of the elements, this would correspond to the value of that specific action. For continuous actions, it's much more common to have the action in approach, where the action is somehow given as an input to the network. So you have to represent it, of course, somehow so the network can easily use it, but then you can do that. Okay, now we talked in the previous lecture about SARSA as TD applied to state action pairs, so it inherits the same properties. What we're doing now is moving towards TD algorithms, right? But it's easier to do policy optimization with SARSA than it is with TD because we have these action values, and therefore we can do policy iteration. So kind of obviously we might want to do SARSA, to learn these action values with function approximation. And indeed, you can do that, for instance, for this small example here. It was done for this small example, which is the game of, well, it's not really a game. It's more of like an example, a benchmark of mountain car. So how does this work? Let me explain. The cart here starts at the bottom or somewhere maybe randomly in this valley, depending on which version of this environment you look into. And the goal is to drive up the hill, and the hill is to its right. There's only 2 actions, or 3, depending on the version of this setting. And these actions correspond to going full force in one direction, full force in the other direction, or not doing anything at all. And this is literally applying forces. So if you pick to go right, that doesn't mean that you'll drive with a fixed velocity to the right. No, it means you're applying a certain acceleration to your cart. So there's a momentum here to the cart. And also, of course, if the cart happens to be driving downhill, it will speed up. If it happens to be driving uphill, it will slow down. It's a very simple physics simulation in some sense. And then the goal is to go up that mountain to your right. But it turns out the car is not strong enough to do that. Its engine is not strong enough. So what the actual optimal policy is to go left first, then start driving down and use the momentum from going down to then drive up the other hill. And this is sometimes used because it's a somewhat tricky exploration problem. If you don't know there's any goals to be had or any like rewards to be attained that are non-zero, it could be quite hard for the car to figure out it should leave this ravine at the bottom. And what we see here now is a value function after a number of episodes. And we see that the shape of that value function changes over time as we add more episodes. The interesting thing that I wanted you to basically look at here is not just the evolution of this value function, but also its shape at the end, which is quite special. It's not a very simple value function. This is because it depends where you are. If you're far enough up the hill to the left, then the optimal value would be the optimal choice would be to go down and then up the other end. But if you happen to be slightly further down, you're not high up the hill enough yet. Then it could be better to go up further. And this also depends on your velocity. If you're here and you have a certain velocity, or let's pick the down, like the bottom part of the valley. If you're here and you happen to have no velocity, then you should be going to the left because we should be driving up this hill first and then down and up the other. But if you're here at the bottom but you do have a velocity, at some point you have enough velocity that your optimal policy switches from going to the left to going to the right, straight to the goal. So you can see these discontinuities kind of showing up in the shape of this value function here, where you can see these ridges. And these are indeed the differences between, am I already going fast enough that I should be going right, and will I then reach the goal very quickly? Or am I too far away and should I be going to the other end? And eventually I'll get there, but my reward will be lower, or my values will be lower because of discounting. So this is a discounted problem, and this is why you can see that the agent basically wants to go as quickly as possible. Alternatively, it's not just because of discounting. You could also, for instance, give a reward of -1 on every step, and you would see similar discontinuities as well. So what was the representation here for this mountain car? It's using tile coding, and I'll briefly explain what tile coding is without going into too much detail. Basically what was happening here is there's these 2 inputs. There's the velocity of the agent, let me go back to this one, and there's its position. And this was basically cut up into small little tiles by discretizing them. Now what tile coding does, so the simplest version of tile coding is just state aggregation. You just cut up the whole space into little squares and you're done. Like this is your feature representation. Alternatively, you could also cut it up into larger squares, but then have multiple of those overlapping. This is similar to what we talked about for coarse coding, where now instead of being in one of these squares, you could be in multiple squares at the same time. One such discretization of the state space we could call a tiling of the state space. And then tile coding could apply multiple tilings that overlap, but they don't exactly overlap, so they're kind of offset from each other. So that you could be in one tile from one tiling, but in a different tile from a different tiling. And if you move slightly, you transition from one to the other tile in one of the tilings, but not in the other necessarily. This is very similar to the circles we saw before for coarse coding. So it's basically the same idea, but with squares rather than circles. And then if you have that, you have some sort of a feature mapping. You can apply linear function approximation to this, and this was applying linear salsa to that. And here's a plot showing the performance of the algorithm, where the y-axis is the steps per episode. So this is not your reward, but it's very related to the reward, except that lower is better. Fewer steps per episode means you're doing better. So this is a measure of performance where low is better. And this is averaged over the first 50 episodes and then also over 100 runs to get rid of some of the variance in the results. And we can see here an n-step approach where there's an n of 1 or 2 or 3, or well, 3 is not there, but 4 or 8. And we can see something similar to what we saw before, where depending on the step size and the n step in your return, you get a slightly different profile where larger n's tend to prefer smaller step sizes, but then for intermediate n's you get the best performance. We saw this before for pure prediction. It turns out to also work for control, that these intermediate values tend to work well, especially if you're interested in a limited amount of data. Note that the x-axis is actually our step size times the number of tilings, in this case 8. So this is a common thing because what we often do if we do something like tile coding, note that all of your features are binary, right? They're either 1 or 0 because you're either in a tile or you're not. So the number of features that are equal to 1 in your feature representation is equal to the number of tilings. And then it turns out it's convenient to basically pick your step size in such a way that takes it into account, because the magnitude in some sense of your feature vector now depends on the number of tilings. This is more generally a useful thing to keep in mind, that the magnitude of the features might matter, and if you're just doing the SGD algorithm, you might actually want to adapt your step size to take that into account. For instance, if you know the average magnitude of your features, maybe you want to somehow adapt your step size to be lower if that magnitude is higher, or vice versa. Alternatively, a similar but opposite approach would be to normalize the feature vectors. Maybe you don't want to do that on a case-by-case basis because that might change the semantics of a feature vector, but you could have some sort of a global normalization, which basically means that the average feature vector, for instance, it has unit length, and that might make it easier to pick your step size. If you don't do this, maybe somewhat obvious in hindsight, if you just consider the same algorithm but you don't take into account the feature vector, then you could consider the exact same algorithm but with different features, where the only difference between the features is that there's some constant scaling. And then turns out the performance is different if you don't take that into account by picking your step size. So that's like a little subtlety that's good to be aware of. In practice, what people often do is they tune the step size to get good performance. For instance, by just running it a little bit of time or running it on some similar problem if you're doing something where you need to do well immediately on the real problem. But often we do these things in simulators, so you can run these multiple times and you could just find out what good values are. And then it's very useful to plot these plots like we have here, which is called a parameter study, where we're basically just not looking at what's the best performance that it could tune, but we're actually looking at how sensitive are these algorithms to different step sizes, n-step parameters, and so on. Okay, that concludes that example. Now we're going to talk more generally a little bit about convergence and divergence of these algorithms. So when do these algorithms converge? What do we mean with convergence? We mean that they find a solution reliably, that they find some sort of a minimum of something. So do they converge when you bootstrap, when you use function approximation, when you learn of policy? And turns out it's a little bit subtle, it's not always the case. Ideally, we want algorithms that converge in all of those cases. Or alternatively, we want to understand when the algorithms converge and when they do not, so we can avoid cases where they do not. And we'll talk about this at some length now. So let's start with the simplest case, which is the Monte Carlo setting. I talked about this already. I mentioned that this is like a sound algorithm, it will converge. So the Monte Carlo algorithm, if we're not considering the stochastic case, we're just going to consider like the loss there first. You can see there an equation which has an argument over something, but let's first focus on the thing inside there. There's an expectation over the policy. This is similar to what we had before. Instead of having a d there, I now put pi there to basically illustrate that the distribution of states, but also the return, depends on your policy in this case. And then we consider this squared loss, which is our Monte Carlo loss essentially. And we want to find the parameters that minimize the squared error. We're going to call that WMC, W for Monte Carlo. And I'm arguing here, I'm basically just stating that the solution to this will be this equation there on the right. This is a linear, this is basically linear least square solution. So if you've seen that before, this will look very familiar. And what we see here that is essentially it's the expectation of the outer product of your features. And that expectation is then inverted. This is a matrix, so this is an inverse matrix, times the expectation of the return times your features. And that turns out to be the solution that Monte Carlo finds. We can verify this, so let's just step through that. When are we done? Like, when is the algorithm converged? Well, it's a gradient-based algorithm, so we are converged when the gradient is 0. Because then, or I should say, if the expected gradient is 0, because we're doing stochastic gradient descent. Because if the expected gradient is 0 of our loss, essentially, the thing that we're optimizing, that means that in expectation we're no longer changing the parameter vector. So when this is the case, then we have reached what is called a fixed point. So we can just state, okay, well, we're going to be at some sort of a fixed point. Let's assume that we don't know what WMC is yet. We're going to derive that here. So we're just going to take the gradient with respect to those parameters, and we're going to say, well, that's going to be equal to 0 when we're at the fixed point. So then we can just write that thing out. So first thing to do is to write out the value estimate explicitly as this linear function that it is. And then we're going to move things around. So first we're going to pull the feature vector outside of the brackets inside. We notice that this inner product times a feature vector can also be written by putting the feature vector in front of this inner product, because this is just a number, right? So we can basically move this one around. But then we can consider this to also be kind of like an outer product times your weight factor instead. Because the order of products here doesn't matter, right? We could put brackets around the inner product here, or we could put brackets around the outer product here. That's the same thing. Otherwise, the x just gets moved next to the return. So we've just pulled that feature vector inside the brackets, that's all. Then we rearrange, and we basically note that this expectation is just one expectation minus a different expectation. So let's move the minus part to the other side. And then we see that this should be equal to that when the gradient is 0. Now all that's left to do is to take that inverse of that matrix on the left-hand side, which therefore is assumed to exist, otherwise this step is not valid. And then we get our solution. So when is that step valid? Well, so there's a distribution over states there, right? And there's an outer product of feature vectors. So when is this typically valid? It's typically valid if your state space is large and your feature vector is small. That's like one case in which it's valid. Because then, assuming at least that your features are non-degenerate, so you have different features for different states, then if there's at least as many different feature vectors that you can encounter as there are numbers in your feature vector, as there are like components in your feature vector, then this inner product typically exists. So this is the common case, essentially. Like typically you will have many more states, and you will have features that do change when you go to different states. And then this this outer product, the expectation of that will typically be invertible. But it is a technical assumption, otherwise you're not guaranteed to converge. It might actually still be that the algorithm still converges, but it might not converge to a point. It might instead converge to a line or a plane if you can't invert that matrix. It depends a little bit on the technical details. So the agent state here does not have to be Markov. This is fully defined in terms of the data. That's kind of interesting, right? So we don't have to have a Markovian feature vector or anything like that. Basically, the fixed point here is defined fully in terms of the xt's. It's not even defined in terms of the agent state. It's defined in terms of the features that you observe. So that's kind of interesting. We didn't need that property. Now we can maybe see if we can do the same for TD. So let's consider the TD fixed point. So I'm going to argue here that this converges to this different thing. Look at it for a second, and I'll go back to the previous slide. So the Monte Carlo thing was this outer product, the expectation thereof, inverted times the return times your feature. This looks quite a bit different. There's a different outer product here. This is still an outer product, but instead of being the outer product of the feature with itself, it's the outer product of the feature with itself minus the next feature. That matrix is inverted if it exists. Under similar assumptions as I just mentioned before, it would exist. It typically exists, but doesn't have to. And then times the reward times your feature vector. Not the return, but the reward. So this is a different fixed point. It doesn't just look different. It typically actually is different from the Monte Carlo fixed point. So now we're going to verify again, as we did for the Monte Carlo case, that this is indeed the fixed point. So we're going to consider the TD update, and we're going to assume that the expected update is 0, where the expected update is given as this. This is similar to what we were doing for Monte Carlo. So we're basically just considering the update, and we're saying, oh, when is this update 0? And then we're just going to manipulate it in a similar way. Here we're again going to pull in this feature vector first, and we put it next to the reward on one end. The step size here is actually not that important, but I'll get rid of it in a moment. So we're going to put it next to the reward, and we're also going to put it next to these two scalars, but we're going to put it on the left-hand side, which we can just do because these are just numbers. And then having put that on the left-hand side, we notice that on the right-hand side we have these WTD. So we can also pull that outside of the brackets, which means we are left with this gamma times xt plus 1 minus xt, both of which are transposed, because they were multiplying with this weight vector. Right? Okay, so now we can again rearrange things. So let's pull this thing to the other side. So there's a plus here, so to put it to the other side, that must become a minus, but we actually fold that minus inside this little term over here. So note that the order has changed. That's because there used to be a minus in front, and we just pushed it inside and instead flipped the order. In addition, let's just pull out the transpose here. Let's pull out the transpose outside of the brackets. So we just first subtract one vector from the other and then transpose it to come up with this outer product. And now finally, we move this part to the other side by multiplying with its inverse, again, assuming that that exists. And we notice that because the learning rate is inside the expectation and we're inverting, for simplicity, for instance, consider here a constant step size, just for argument's sake, but you can get rid of it in other ways. We can see that this step size will actually cancel out with that one, because moving this one to the other side by multiplying with the inverse kind of means we're multiplying with 1 over the step size, which cancels out with this step size. So we get that the fixed point becomes this one. So this is kind of just verifying that the fixed point is indeed the one that is listed above. And we have like substantial proof these days that this is indeed where TD converges, if it converges. It's important to note that this differs from the Monte Carlo solution, and typically the Monte Carlo solution is actually the one that you want. Why? Well, because the Monte Carlo solution is defined as minimizing that thing that we actually want, right? This is actually minimizing the difference between the return and the value. This is sometimes called the value error or the return error. And this is an unbiased, the gradient of this is unbiased with respect to the using the true value instead of the return as well. But actually one could also argue that we don't actually even care about the true value, we just care about having a small error with respect to the random returns. That's also valid. So this seems to be exactly what we want in some sense. And then if TD converges somewhere else, this might be undesirable in some sense. And this, I think, in general is quite true, that Monte Carlo typically converges to a better value than temporal difference learning does when you start using function approximation. However, temporal difference learning often converges faster. And of course, we can trade off again. We can pick an intermediate lambda or an intermediate n and kind of get the best of both worlds. You could even consider changing this over time. You could start with a small n and then slowly increment it over time, and in the end, in the limit, maybe still come up with the Monte Carlo solution, if you'd like. So there's a bit of a trade-off here, bias variance trade-off, again, similar to what we had before, but now TD is biased asymptotically as well. In the tabular case, this is not the case. In the tabular case, both Monte Carlo and TD find the same solution, but if we add function approximation, even just for linear function approximation, TD remains biased, which means that it actually finds a different solution in the limit. So it does converge if it converges to this fixed point. And we can actually characterize that a little bit farther by considering the true value error, which is defined as this difference between the true value and our current estimate, weighted according to this distribution over states, where here we use dpi to denote that this distribution depends on our policy. And then Monte Carlo actually minimizes this value error completely, but TD doesn't. But we can say something about where what TD reaches. And we can say that the true value error of TD is bounded in the following way, where it's smaller or equal to 1 divided by 1 minus gamma times the value error of Monte Carlo, which is equal to the minimum value error that you can get. under any weights. So what is this saying? Well, this is basically saying that TD is doing maybe a little bit worse asymptotically than Monte Carlo. It's doing something different, right? It's biased, but we can bound how bad it is. Now, how bad is that? Well, there's this term 1 divided by 1 minus gamma. How big is that? Well, this depends on gamma, obviously. And there's this useful heuristic that we briefly talked about earlier in the course as well, where you can kind of view this as a horizon, where if gamma is 0.9, for instance, then 1 minus gamma is 0.1, and then 1 divided by 0.1 is 10. So if your gamma 0.9 roughly corresponds to a horizon of 10, so that means that in that case, if your gamma is 0.9, the Monte Carlo error can be 10 times smaller than the TD error. But at most, right? It can be at most 10 times smaller, because this says that the error that TD reaches is smaller or equal to this thing, right? So it could be, of course, in some cases, you can have feature representations, for instance, for which TD actually happens to find the same solution as Monte Carlo. This is just saying in the worst case, if, for instance, your gamma, your discount factor is 0.9, in the worst case, it could be 10 times larger. Doesn't mean it necessarily is 10 times larger. Now, you may have noticed that I already said a couple of times, if it converges. So there's a slight, well, but potentially big problem here. There's a fundamental problem, and it's a really interesting one. And it's related to the following fact, that the temporal difference learning update is not a true gradient update. And this is due to this, it's highlighted lightly in the slide here, to this bootstrapping, because the bootstrapping uses the same parameters as the parameters that we're updating with this update. But we're kind of ignoring that in the update. We're basically just plug that in as a proxy for the real return and hope for the best in some sense. But I'll show you an example where this can go wrong. Normally this is okay. It's okay when I say this is okay. I mean it's okay that it's not a gradient update. Sometimes people like things to be gradients because we understand gradients quite well. We know that stochastic gradient descent converges. So if we have something that's not a gradient, it sometimes is of some concern. So it's good to appreciate that there's this broader class of algorithms called stochastic approximation algorithms, which include gradient algorithms, stochastic gradient descent, as a special case. But that's not the only special case that necessarily converges. And indeed, temporal difference learning can converge to its fixed point. So stochastic approximation algorithms are a broader class, and there are specific conditions under which these do converge. Stochastic gradient descent always converges under fairly light assumptions, such as that the noise is bounded, the step size decays, and your data is stationary, and so on. But temporal difference learning does not. And now I'm going to show you an example in which it doesn't. So this is an example of divergence of temporal difference learning, where we have two states. And our feature vector has exactly one element. And this feature vector has an element equal to 1 in the first state, and this same element is equal to 2 in the second state. What this means is depicted above the states, is our value estimate in the first state is just w, because it's just this number w, which is just also a single number, because our feature vector is also only has one element, right? And we're doing linear function approximation here. So our value in the first state is w, and the value in the second state is 2w, because it's just the same number w times your feature, which is 2. The reward along the way is 0. It's a simple problem, but now we're going to consider it's a partial problem, right? I didn't say what happens after you reach a state where the feature vector is 2. I'm just going to consider this one transition, and then let's see what happens if we apply TD. So let's step through that. Let's just first write down the TD equation. This is our update for the temporal difference, the temporal difference learning update for our parameters of the value function, where the value function gradient in the linear case is just our feature. And in this case, the reward is 0. The value of the subsequent state, S prime, is the value of that state on the right, which is 2w, for whatever w is currently. And the value that we're updating, so the value of the state that we came from, is just x times w, where x is 1, so that will just be w. So we've just filled in these numbers here. This 0 goes over here, this 2w goes over here, or maybe more precisely, this 2 goes over there, and then the w comes in because we want the value estimates, and then this 1 goes over here, so there's 2w minus 1w, with a discount factor as well. And we can slightly rewrite this by pulling out the w and getting rid of that 0, which we don't really need to consider. So then it turns out that this update looks as follows, where we have our previous weight estimates plus your learning rate, whatever that is, times 2 minus discount minus 1, times whatever your feature vector is. Whatever your weight vector is, your weight number, which only has one number here. But what does this mean? Well, let's consider that your weight is positive. Let's say you initialize it at 1. And let's consider a discount factor which is larger than a half. If the discount factor is larger than a half, this term within the brackets will be positive. If your weight is positive and this term within the brackets is positive, and again the weight here is positive, all of this will be positive. And in fact, this whole term here on the right will be added to the previous weight, which means our new weight will be larger than the previous weight. But the weight was already positive, so we're moving away from 0. Note, the true value function here would be 0. Like the true value of that first state might be 0. At least it's consistent with this transition for it to be 0. You can expand this example to actually have a fixed point of 0. But in this case, it will just continue to grow, and your weight in the limit will actually reach infinity. What's actually even worse, it tends to grow faster and faster as well, because your weight keeps going up, and this term multiplies with your weight. So this is an example of a problematic behavior of temporal difference learning. And now we can dig into why this has happened, when this has happened, how can we characterize this, and how can we maybe avoid this. So what's happening here is that we're actually combining multiple different things at the same time. We're combining bootstrapping. We're bootstrapping on that state value on the right. We're combining off-policy learning, and I'll explain that a little bit more. And we're combining function approximation. And when you combine these 3 things together, you can get these divergent dynamics. This is sometimes called the deadly triad, because you need all 3 for this to matter, for this to become a problem. The off-policy learning, I promised I would say something about that. Why did I say this is off-policy? There's no policies here, there's no actions here. So what's happening here? Well, there's a certain dynamics, and your dynamics would get you from this one state to the other state. But then what we're actually doing is we're going to resample that transition over and over, and we're never going to sample any transitions that come from the state that we've entered just now, right? And that is off policy in the sense that in this case, there are no policies that would sample the states over and over in specifically that way. So what we're doing instead is we have an off policy distribution of our updates. This can emerge, why this is called off policy, is this can emerge if you're trying to predict the value of a certain policy while following a different policy. For instance, it could be that the value from this state, that there are actions, but we're just not interested in their values. And hence they get kind of zeroed out in your update in some sense. Now, we could also consider on-policy updating by extending the example to be a full example. And now we consider this second transition as well. And let's, for instance, assume that this transition just terminates with a reward of 0. And then maybe you get transitioned back to this first state. So maybe you just see this episode over and over and over again. But now we sample on policy, which means we actually sample the transition going from this second state as often as we sample the transition going to that state. If that is the case, turns out the learning dynamics in general are convergent. TD learning will converge also with linear function approximation if you're updating on policy. I will show that here just for the example where we can just write out maybe the combined update for simplicity. So let's just consider this transition and let's immediately consider that other transition, and let's just write down both of those updates, where the second transition bootstraps on the terminal state with value 0, also has a reward of 0 along the way. So this will then basically only retain that value of that state. And if we merge these together, we get this update to our weights. And note that the term inside here is now negative for any discount factor smaller or equal to 1. Which means that if your weight happens to be positive, it would push it down. If your weight happens to be negative, it would push it up. And that is exactly what we want in this case, because the optimal weight here is 0. Just in this example, right? Not generally the case, but in this example it's 0. And we can see that the dynamics are such that indeed, if you're larger than 0, you will get pushed towards 0. If you're below 0, you will also get pushed towards 0. So this seems to be working. And indeed, it has been proven in general that on-policy temporal difference learning with linear function approximation will converge to the optimal policy. The optimal values in terms of its fixed point, right? So the fixed point of TD is still different from Monte Carlo, but if we consider that fixed point to be the goal, it will find that fixed point in the on-policy case. as I mentioned, the multiplier here is negative for any discount factor between 0 and 1. Okay, so off policy is a problem, on policy fixes it. Let's dig into one of the other aspects. I also mentioned function approximation as one aspect of this. So let's see what happens if we don't do function approximation. So we can consider a tabular representation where in each state we do have a feature vector. I've basically just denoted it as a feature vector, but it's one hot picking out exactly that state. If we do that, this is just regression and this will also converge. The answer might be suboptimal, but no divergence occurs. So again, TD might have a different fixed point. In the tabular case, it doesn't actually have a different fixed point. In general, it can have a different fixed point, but we could, by playing with the representation, we could go from divergent dynamics to convergent dynamics. That's the point here. Tabular being a special case. So we can still update off policy now, importantly, right? We don't need to update on policy, so we can go back to just updating the first state. If we would do that, then the value of that state will converge to whatever the discounted value of the next state is, and we would never update that value. So this is a different way in which you can have a different answer, because we're considering off-policy learning. Of course, with function approximation, this can also interact. But even in the tabular case, it could be that because you're learning off-policy, that you simply ignore certain states, and therefore never update their values, which might have lingering effects in the tabular values of the other states. So that's just like something to maybe be a little bit aware of. This can still affect where your solution is, but you won't diverge. You'll still converge to something. So that was two. We had off-policiness, on-policiness. We had function approximation or not. And now let's go to the third one. What if we don't bootstrap? Or what if we bootstrap less? Because I said there were three. Off-policy learning, function approximation, and bootstrapping. Now let's look at the bootstrapping. And one way to not do bootstrapping is to use multi-step returns. So let's consider now to have a lambda return. We're still considering off-policy updates, right? So we're only sampling this one transition over here in some sense. But instead of calling it just sampling that one transition, let's say it a bit more precisely, we're only updating this first state. We're never actually updating the second state. But now let's consider taking a lambda return from that state instead of taking a one-step return. This is again something that can happen in some sense in the wild in off-policy learning. And then we can just write that out. We have the lambda return here, which we know bootstraps slightly on that first state and also slightly continues. But it continues to VS double prime, which in this case is this terminal state. So S prime here is this second state, and S double prime is then this terminal state. So now we can fit in all these numbers that we know. We know that the reward on every step is 0, so R is R prime is 0, and also the value of this state after 2 steps will be 0. We can just fill in all the numbers that we know, and we get this thing. And now we can analyze that thing. So it's very similar to what we had before, but before lambda was basically 0. So before, when we were talking about the divergent example, we had 2 gamma minus 1. Now we have 2 gamma times 1 minus lambda minus 1. We have a parameter that we can play with. We can play with this lambda parameter. Turns out we can always make sure that this multiplier is negative, which we need here for convergence, if we pick the lambda parameter in a specific way. So what we want is essentially that this whole term is negative, which means that we want this term to be smaller than 1. Then we just rearrange, move things around, and it turns out the condition for that will be that your lambda is larger than 1 minus 1 over 2 gamma. Just to be clear, this is not a generic finding. This is just specifically for this example, this relationship. We're just going through the example. So for instance, we could pick a specific discount. We could pick discount being 0.9. Then turns out the lambda parameter that we need to ensure that we have convergence is that you need to pick it larger than 4 over 9. You can just figure that out by plugging in 0.9 here, and then just doing the math and figuring out what the what the trace parameter lambda should be. This is not a hugely large trace parameter. Typically people pick things like 0.9 or 0.8 or something like that. So 0.45 is not an unreasonable value to have. If you pick it larger than that, you're good to go and you won't diverge. So these are important things to keep in mind. And one thing that I want to highlight by going through all of these things is that it's not always binary. So the deadly triad might make it sound that if you combine bootstrapping, function approximation, and off-policiness, that you're always in trouble. That's not actually true. You can combine bootstrapping, function approximation, and off-policy learning, as long as you're not bootstrapping too much, you're not too off-policy, and your function approximation is tabular enough in some sense. So what turns out to be the case is that people run these algorithms in practice quite a lot. And a lot of deeper algorithms actually combine all these three things. They combine bootstrapping, off-policy learning, and function approximation, where the function approximation is, for instance, deep neural networks. The off-policy is, for instance, because we try to predict many different policies, or because we're trying to learn about past data and things like that, or because we're just doing Q-learning at scale, which is also an off-policy algorithm. And then the bootstrapping is also because of, for instance, doing Q-learning or doing something similar, but also because of this bias variance trade-off that we typically find that it's better not to bootstrap too heavily, but also not to use full Monte Carlo returns. So we're combining all of these, but turns out many of these algorithms are actually stable and they do learn well, because we're still in the triad, but we're not in the deadly portion of the triad. An alternative that you could consider is to pick a different loss. So let me briefly go into there. So temporal difference learning has a specific update, right? And I mentioned, oh, temporal difference learning can diverge if you're doing all of these things at the same time. But why do temporal difference learning? Can't we find something else, maybe? Okay, so the problem, as mentioned, with temporal difference learning is that it ignores essentially that we're bootstrapping on a value that itself depends on the weight. What was happening in the example that we had just now, going from a state with value w to a state with 2w, was essentially that we're trying to update this state closer to the value of that next state. But in doing so, we're actually updating the value of the next state more away from us. So you're chasing your own tail, except that your tail is running away from you faster than you're running towards it. That's why TD, in that case, diverges. So an alternative would be to actually define something that is a gradient. A true gradient. One example of this is the Bellman residual gradient algorithm, where we define a loss which is just our square TD error. So this is a different loss, right? We don't have our normal value loss here. We don't have our normal value error. We instead say, well, let's just consider the temporal difference error and let's see if we can minimize that. If you push the gradient through that and you calculate that, you find something that looks very similar to TD, but has a different additional term. Unfortunately, this tends to work worse in practice. And one reason for that is it smooths your value estimates, whereas temporal difference learning in some sense predicts. So what do I mean there intuitively? Temporal difference learning updates the value of a state towards something that is in the future, towards this one-step estimate of your value in the future, the reward and the value of the next state. This algorithm instead, it's a fine algorithm, it can be used, and it's convergent in as much as temporal difference learning, as stochastic gradient descent is convergent. But it does something that is maybe a little bit weird, in the sense that it updates not just the value of the state that we came from, but it also updates the value of the state that we're bootstrapping on. So in that sense, it's a smoother, because what it might do is actually it might pull down, for instance, the value of a state that you're bootstrapping on, just to make it easier to predict it. But that doesn't mean that's a valid value for that state. So it turns out if you run these algorithms in practice, oftentimes it just works worse. That's maybe not a necessity, maybe it's not necessarily worse, but it basically seems to be that this loss, although we can define a gradient of that loss, which looks somewhat similar to the TD algorithm, that maybe the loss is just not the right thing to be minimizing. It might not be the right thing to look at. So smooth values are not just bad because your value accuracy might be slightly wrong, but it might also actually lead to suboptimal decisions. This is especially true if your rewards are, for instance, sparse, because then there might be this one rewarding event, and immediately after getting the reward, your value function maybe should drop because you've already received that reward. But if you do something like Bellman residual minimization, what might actually happen is it tends to smooth over that discontinuity in the value function, and hence the states immediately after already taking the reward might be updated to look a little bit like they might still be able to take some of the reward, which might lead to wrong decisions. So let's consider a different alternative. Let's, instead of squaring the TD error inside the expectation, let's just take the expected TD error and try to minimize that. If we minimize the expected TD error, maybe we're still kind of good to go from a prediction perspective. And instead of let me just go back a slide. Let me show the one difference here is where the square is, right? So here in the Bellman residual algorithm, the square is inside the expectation. Here, when we consider the Bellman error, the square is outside of the expectation. Again, we can take the gradient of this, But there's a catch, and the gradient looks very similar to the previous algorithm, but there's this weird S prime there. S prime is a second independent sample of S t plus 1. So S prime t plus 1 needs to be sampled separately. If you don't sample it separately, you're actually doing this other algorithm that we talked about before, where S t plus 1 is the actual next state that you've seen. So this algorithm can only be applied if you have a simulator that you can reset. You should be able to sample the transition twice, essentially. And then you could apply it, but that's an unrealistic assumption for many cases. If you're a robot in the real world, and you're just interacting with the world, you can't resample a transition twice. So then this algorithm becomes less feasible. Here's just a brief summary of what we were just talking about. There's a couple of different categories. So you have your algorithm, it could be Monte Carlo, or it could be TD, you could be on policy, or you could be off policy, and you could pick a certain function class. Now, in terms of just summarizing the convergence properties of these algorithms, if you're on policy, you're mostly just good to go. The only thing that's not 100% guaranteed is nonlinear convergence. But even for that one, we can say some things actually, and in some cases you can guarantee that TD converges for the nonlinear case, but it requires more assumptions. So we can't say in general it always converges. If we go off policy, we see that linear function approximation also becomes problematic for TD. Although again, I want to stress that this doesn't mean it's always a problem. It just means there are cases in which we can't guarantee convergence. Doesn't mean the algorithm doesn't work in general, just means that there are edge cases in which it could do something wrong. This has been addressed in more recent work that is too detailed to go into in this lecture, where people have devised new algorithms that are slightly different from TD, but might be inspired by TD, that are actually guaranteed to converge, also with function approximation, also under off-policy updating. But those algorithms are beyond the scope of this lecture and this course, actually. Okay, so now let's move towards control. So now that I've maybe expressed some uncertainty about convergence, but also some evidence that it typically does converge. So we can extend all of these control algorithms, obviously, to function approximation. The theory of control with function approximation is not that well developed, unfortunately. This is because it's substantially harder from a prediction case, because now the policies under your direct control, this might change over time, and it might be quite hard to reason through. Maybe the one exception of this will be in a subsequent lecture when we talk about policy gradients, which are again stochastic gradient algorithms and therefore are in some sense fine. But the theory of control with function approximation when you use value estimates is much harder in some sense. In addition to that, actually we might not even want to converge that often or during learning, especially when considering this value learning, because you might actually want to continue tracking. So for instance, if you're doing something like value-based control, your policy will be changing. So your predictions shouldn't converge because they want to converge to whatever the current value of the policy is. But if the policy keeps changing, you actually want to track that rather than converge. But also more generally, even if we're doing direct updates to the policy, it might be preferable to actually not converge, but just to continue to adapt. That doesn't mean that convergence guarantees are not interesting or not important, because one thing that we could still have is if we have a guarantee of convergence, that means that the algorithm kind of updates stably, typically, throughout its lifetime. Whereas if you can diverge, you only need to diverge once for everything to fall apart, obviously. So understanding when things converge and diverge is still very important, even if we can't fully characterize it. Okay, now moving on, we're going to consider updating these functions in batch settings. So we've talked about batch methods previously, but there's a different reason we're going to talk about it now. Previously, when we talked about batch reinforcement learning, this was basically to highlight differences between temporal difference learning and Monte Carlo learning. But we weren't proposing it as an approach that you should necessarily follow, although we did mention that you could do that. Now we're going to take the other view, which is, oh, what if we really want to learn with batches of data? And a reason why you might want to do that is because, well, gradient descent is a simple and appealing algorithm. It's not very sample efficient. The reason why, intuitively, is that every time you see a transition, you're going to consume that transition and make maybe an incremental update to your value function. And then you're going to toss that transition away. But there might be a lot that you could have learned from that transition that you can't immediately extract. It doesn't play a role immediately in the update that you're doing. And then that would be a waste in a sense. So instead, we could consider doing a batch approach where we try to find the best fitting value function for a set of data that we've seen so far. So instead of just doing one gradient update necessarily on every sample, we could try to maybe extract as much information as we possibly can from the training data. There are several ways to do that. I just want to mention that if this seems at odds with our main goal at the beginning, where the world is large, your lifetime is large, and you consider a robot walking through the world, maybe you're thinking, well, that robot can't store all of the data. This is true, and I agree with that viewpoint. So full batch settings are maybe most typically employed when the data is not too huge, but turns out you can also employ them in practice by, for instance, storing only a limited amount of data. Or alternatively, this will actually also be related to model-based approaches where you can consider storing some of the data to be quite similar to storing an empirical model. So now it's just a choice of what your model is, what the structure of your model is. Is it a parametric model or is it a non-parametric model that consists only of data that you've seen? So there are approaches that feel quite similar to these batch approaches that do scale to really large problems where maybe you couldn't store all the data. But for now, for simplicity and clarity, we're going to focus on this case where we really are going to consider all the data. And we will actually see that there are some methods that don't actually need to store all the data to get the same answer. And we're going to start there by considering again the linear case. So we have linear function approximation. And we were considering fitting the best possible fit of our parameters. So we talked about this before in the limit for TD. So let's consider that TD update again, and what we said is, if you consider the update to have converged, so that the expected update is 0, then your fixed point will be this weight vector, which we called WTD, which is as defined on the slide. This is the same as we saw earlier. Now, one idea that you could do is, well, what if we take that expectation, and instead of taking the expectation over all possible states and all possible transitions that could happen, let's just take it over the things that did happen. So what we'll do here, we're at some time step t, and we're just going to, instead of taking the full expectation, which we don't know, for this you would need the knowledge of the Markov decision process, instead what we're going to do, we're going to take the average of the things that did actually happen. So this is very similar, and in the limit, of course, this average, if time grows to infinity, if your distribution is stationary, which needs to be the case for this expectation to even exist, then this summation, this equation actually will converge to this equation above by law of large numbers, assuming of course that the variance of your reward is finite and so on. So the idea then is to maybe, instead of doing this where we just use this for analysis, we are going to do exactly the same things on the empirical loss. And that turns out this will look as follows, where we see something very similar as we did for the TD fixed point. So for the TD fixed point, let me walk you through that first. We had the expectation over an outer product of two vectors. So the first vector is just your feature vector, and the second vector is your feature vector minus the next feature vector discounted. And this is an outer product, so this is a matrix. And the expectation over that will be a full rank matrix, typically under some mild assumptions, so we can invert it. And then we multiply that with a vector. So we have a matrix, number of features by number of features, times a vector, number of features. And that will give us a weight vector. This is also the number of features large, which fits with the linear function approximation, of course. Now here we're going to do exactly the same thing, but instead of having the expectation, we have summations. Note that we're not taking averages, because if we would put like a 1 divided by t here, and we would put 1 over here, they would just cancel out, so we can ignore that. We can just consider the sum of these outer products and the sum of these vectors over here. And that would be equivalent to taking the average instead. So the summation is over exactly what you would expect now, which is this outer product of these feature vectors, but it's not for the expected feature vectors, it's for the ones that you've actually seen. And then again here the same thing happens. This is called least squares temporal difference learning, and the solution here, this weight vector, is the least squares solution given some data. So we can put that equation here at the top of the slide, where I made one change. Here in the previous slide I called it WLSTD, and now I'm just going to call it WT, because in fact we can change this. As we get more data, WT can change, because it's just a data dependent weight. And indeed we could be interested in these predictions for any time step during learning, right? So there might be reasons why you might want to extract this prediction, for instance, for reasons of control. You might want to pick actions, although that's a bit more subtle to combine with least squares temporal difference learning, because in some sense you don't want to consider all the data then, because this is collected over past policies. So for simplicity now, consider the prediction case, but it could be that you still want to know these value functions as you go. So you might want to have this weight vector, you might want to compute it, you get some new data, you want to recompute it. Now, fortunately, we can do that online. So before we do that, let's just give these things names. We call the matrix here inside the brackets A, so that this whole thing will be A inverted. So AT is just this summation of outer products. BT will be this summation of the feature vector times the reward. So these are the names we give it, and then the weight vector at every time step is defined as the inverse of AT times BT. Now we can update both of these online. So we're considering actually storing both these separate quantities, and we're going to update AT separately from BT and then recompute WT whenever we need it. One way to do that, the naive approach, and maybe the most obvious way to do that, would be to update the A matrix by just adding the current outer product, the one you've just observed, and adding the reward times feature vector to the B vector. Unfortunately, the reason I call this the naive approach is that it's fairly expensive. It's not expensive because of the B update, that one's very cheap, because that one just has the same number of operations as you have features. X here is just a feature vector, B is the same size as a feature vector, we're just adding two vectors together, and this gives us our new vector. The update to A is more expensive, because we're adding an outer product, which will be an outer product of these feature vectors will be the same size as a matrix by features by number of features. And we're adding this to this A matrix, which is also the size of the features squared. So adding these together and giving us our new A matrix is n squared, where n is the number of features. So that is also not the most expensive operation here. The most expensive operation is then that when we want to compute W, we need to invert A. And inverting A naively will give us a cubic cost, because A will be some dense matrix, and inverting a square matrix of n by n will be cubic in n. So that's expensive, and we want to avoid that. And the reason we want to avoid that is because we want to ultimately consider large feature vectors. So if you only have 10 features, you could apply this approach, right? Then the algorithm would cost like 100 computations to compute your weight vector. 1,000 computations. Updating B would only be like 10 operations, order 10 operations. Updating A would be order 100 operations, but then inverting A would be order 1,000 operations. That's still okay. But if you have 1,000,000 features, this becomes very, very wild very quickly, and it's not very scalable approach. So we'd like to do something a little bit cheaper. Turns out you can do exactly the same thing cheaper by updating the inverse of the matrix A instead of the matrix A itself. And this is called a Sherman-Morrison update. And Sherman-Morrison is a more generic approach where we can take any matrix and then add any outer product and then consider the matrix that results from that operation. And then turns out the inverse of that matrix can be computed in only squared number of operations if you knew the inverse of the matrix that we had before. So we always have this because we're incrementally keep on updating it. So we just start, for instance, A you could start, for instance, at something simple like the identity, and then you could just incrementally keep on updating like this. So the operations here are, as you can see, a matrix by another matrix. Here's an outer product by another matrix. Of course, you could also first compute the dot product of the vector with the matrix, turning that into a vector, and then you still have the same happening here. So then you'd still have an outer product left. The thing below the division bar is just a scalar, because it's a vector times a matrix times a vector plus 1. So this is it looks maybe a little bit complicated. There are many proofs of why Sherman-Morrison works online. Feel free to dig into that if you didn't see this before. The update to B remains the same. We don't need to invert B. It's just a vector. You can't invert that. And this way we would be able to compute this W, this weight vector at the top of the slide, by incrementally updating the inverse of A rather than A itself. This is still quadratic in the number of features, and it applies only to linear function approximation, but it is an approach that scales at least to some larger numbers than the cubic approach. It is more compute than TD, so in large applications this is still avoided for two reasons. One is that it's limited to the linear case, as I mentioned, and the other one is that you might still want to have very large feature vectors even if you want to do linear. And if your feature vectors are size 1,000,000, then still squaring that is still fairly large, so it might still take quite a bit of time on every step. However, it could be that this is feasible for your application, and then it's good to keep it in mind. The other reason why we talk about this is because it can be an inspiration to other approaches. So in the limits, it's good to appreciate that LSTD and TD converge to the same fixed point. For LSTD, this is almost immediate. Let me just go back a couple of slides to show that, because as I said, by the law of large numbers, this thing will just become that thing, which means that the solutions will also become the same. So LSTD kind of immediately will converge to the same fixed point as TD under mild assumptions. And we can extend LSTD to multi-step returns as well. We could consider LSTD lambda instead of just considering the one-step LSTD that we discussed just now. It can also be extended to action values, maybe quite naturally. You can almost always extend anything that's defined for state values to state action values by considering SARSA-like approaches. And then, of course, we can interlace it with policy improvement if we do that. We could have least squares policy iteration, where we just use LSTDQ to estimate action values for the policy evaluation phase, and then we greedify the algorithm. Of course, when we do that, when we change the algorithm, we need to be a little bit careful that we then shouldn't use all of the data collected so far for computing our value estimates. One simple approach could, for instance, be that you just restart the policy evaluation phase whenever you've made a policy improvement step, throwing away the past values, not trusting them anymore, and just recomputing them for the new policy. Okay, now we're going to move on to what is maybe a more generic approach, but it's similar to LSTD in the sense that we're going to consider the data collected so far. So we consider that we have some experience, a data set consisting of all of our experience up to some time step t. Now, one thing we could do is, instead of considering all of these transitions at once, as we were doing with LSTD, we can just sample transitions from this data set repeatedly. So we sample a transition that's enumerated with a time step n, which is smaller or equal to the current time step t. And then we just do a gradient update with that. So if this data was collected under a certain policy and we're interested in evaluating that policy, this seems like a fine approach. You can actually also combine it with Q-learning, and I'll show that in a moment, to learn off policy. The benefit of this is that you can reuse old data. So you could just store all of the data you've seen so far and keep on updating, which means you could take multiple steps on the same, multiple gradient steps, incremental gradient steps on the same transitions over and over, and thereby extract more knowledge that you maybe could do from a single gradient step. This is also a form of batch learning. It doesn't consider all the data at once. It doesn't consider the full batch at once, but instead it considers the batch to be able to sample from it. Of course, you have to be a little bit careful that if your policy changes, this might be important, because if you're just trying to do prediction, you don't want to use transitions for a policy that has now changed. Or alternatively, in a future lecture, I'll talk about how to deal with that and how to still be able to use it, but to reweight it appropriately. Okay, this brings us to the exciting topic of deep reinforcement learning. I will touch upon that only briefly now. There will be much more about this in later lectures. So I'm going to start by just doing a very, very brief kind of a recap on neural networks in general. This might be very familiar to many of you already, but it seemed useful just to very briefly go into that a little bit. So let's go to the note-taking app that we've been calling a Blackboard. And let's consider what deep neural networks essentially are as far as we're concerned. There's a lot to say about this, and of course I won't be able to say anything remotely scratching the surface, but let me just give you the very bare minimum that might be useful for us to understand for the purposes of this course. So what have we been considering so far? Let's first start with the linear case, and we were considering to having a value function that is defined as an inner product of some weight vector w with some features of the state. Now, this is a linear approach which has benefits and downsides, as discussed before. But what would be a nonlinear approach? Well, for instance, we could have some function, let's say f, that takes some number as input and outputs a real number. And we could apply that, we could say that any such function, actually let me make it clear that these are both just numbers. So any such function, let's just assume that without bothering, if we apply this to a vector, then it'll be applied element-wise. So the idea is that we have some function which is nonlinear. Popular examples of this include, let me just draw a couple, squashing functions. So if this is the 0 lines of a graph, then the squashing function might look like this. Or another popular choice these days is what they call a rectifier linear unit, which has a discontinuity that looks like this, where essentially it's this one is just defined as f y is max 0 y. And the benefit of this is that it's linear in some part, but it has a nonlinearity, so you can use this to add nonlinearity to your function if you want. And I'll show you in a minute how. This one's often called a sigmoid, or the one I actually, this is a more general term, the one I drew here, or kind of tried to draw here, kind of is a 10H. So those are just specific functions, and the idea is that this is some nonlinear function, and then one way to make that value function nonlinear is just to apply that function. So we could consider something like this, where we have a function applied. Now this is not particularly useful yet, right? But it's already nonlinear, and if f is differentiable, then we can still compute its gradient with respect to the weights. Now this is not very useful immediately. Why would we necessarily, for instance, squash the function between 0 and 1 as we do with the 10H? Or why would we say, oh, negative values are not allowed, as we do with the rectifier? So this one's called a rectifier linear unit. No, so this is not typically what we do. So let me immediately correct that. Instead, what we might do is we might say, well, let's first apply some matrix to our features or inputs. Sorry, we don't need a transpose there. So I was starting to draw a transpose. And then we multiply this again. So let me call this matrix 1. And then we have maybe a vector 2. And this could be our value estimate. So now note that if we want to take the gradient, so the gradient with one of the components of W2 will be quite simple. So if we consider the partial derivative of VW of some state S with respect to W2I, this will simply be the function f applied to this weight matrix applied to our feature vector taken at I. So note here that this weight matrix multiplied by the feature vector is a vector, the matrix is a matrix, so the output of this is a vector. So f is applied element-wise, and we're basically going to subscript this with an I to denote that we're taking the ith input, the ith output here. There's different ways to denote that. I could have also written this, for instance, with index notation like that. So that's very similar to before. Essentially, as far as we're concerned now, in terms of the derivative with respect to the weights in W2, these are just features. So our features are now defined as some function f applied to some weight matrix W times the feature vector. And those are, as far as we're concerned, just our features. But the difference now is that we can also consider, as part of our update, the gradients, so the partial derivative with respect to some element in matrix 1. So let's consider, for instance, I and j. So it's a matrix, right? So we need to index twice to get one element. And this can be computed just by the chain rule. So what we'll get is essentially that we'll have the gradient of W VW by the intermediate thing. So we take the gradient of the intermediate thing being this one taken at I, and then that thing the gradient with respect to that weight. But let's do an intermediate step. Let's take it first just to the inputs of that function. And then finally we have so let's unpack this a little bit. So this part, this first partial derivative, is just the gradient of our value function with respect to the ith feature in some sense. This will just be W2 at I. This next part is just the derivative of our function, whatever that is. And these functions above, they always have some well-defined derivative. The ReLU doesn't actually have a well-defined derivative at exactly 0, but that's okay, we just define it to be 0 there. So we extend this to have a well-defined derivative at 0, so that the derivative at least is not discontinuous. Apologies, sorry, let me move down again. So this will just be the derivative taken at whatever those values were. And then this last bit, the weight matrix times the feature vector by that one element, will simply be feature vector indexed at that one element. So these are all just numbers now. Sorry, this one's also taken at I. So note that actually what we're considering here, so I've indexed here, let me use a different color to denote that. Here I've indexed with I, which I did here as well. I could also have written that as this, like the F is applied to the weight matrix, but indexed at I. So let me just say I dot. So now it's a vector. So that's a different way to write that same thing. So essentially, whenever I index here, so let me actually pull that one inside. Let me get rid of that one over there, and let me instead put it over there to make it clearer that we're actually indexing the weight matrix. Now note that the things that we're left with then at the bottom, they're all just numbers. This is a number, that is a number, that is a number. And we just multiply them together to get that one number that we needed for our gradient. Then our gradient is just this one big vector which merges both the contributions for the second weight vector and for the weight matrix. And we can continue stacking this. Now I mentioned before it's useful to go through these steps to apply the chain rule a little bit, but you don't have to actually worry too much about that in practice these days, because what we instead do, we just, whenever we need a gradient, we apply a software package which will automatically compute that gradient. So you can make these functions arbitrarily complex. So one thing that you could do is, for instance, you could have a value function that has some weight, let's say at layer L, times the feature, sorry, so this is just some function which we could also subscript L, where this is a layer index. And then this will be times the inputs, let's call those y at layer L. And then we could just say, oh, the inputs at layer L are defined as some weight matrix. L, this is a vector, so now we have a matrix of L minus 1 times the features at the previous. So we can stack this fairly deeply. Just to expand it for one specific example, let me just write it down explicitly because it doesn't hurt to have that in mind. For instance, we could have something like 3 layers, let's say. And the more layers you add, when we use terminology in deep learning, we say the deeper your network is. This is because you can denote this function, you can denote that as there being an input, x, and then there's a weight matrix here, and then we get our, let's say that like, let's give this a name, sorry. Ran out of space there on the end. Let's give this one a name I1, then this could be I2, and then you could do that again, I3, and then maybe then, so we could denote this as well by showing that there's lots of connections here. This could be a dense matrix operation, and then in the end maybe it goes into a single number. Where this is weight 3. So the idea is that you can stack these. People use all sorts of notations to denote these neural networks, sometimes as simple as something like this. Or sometimes people draw more complicated figures which show the dimensions a little bit better. As you can imagine, you can make these things fairly complex and weird looking as well. So you could have all sorts of weird structures which merge in strange ways, because maybe you want to somehow put some inductive bias in the structure of your value function. This can be useful in some cases. This is a way to put, for instance, some more prior knowledge into your function class, if that is helpful. It could also be that you have multiple inputs that maybe come in at multiple places. For instance, you could have vision inputs and auditory inputs, and maybe the vision input has a certain pre-processing necessarily, and then the auditory inputs have a different pre-processing necessarily. So you could have all sorts of inputs, like maybe this is some part of your observation, this is a different part of your observation, maybe this is yet another part of your observation, and they finally all come together to give you your value estimate. And then all the parameters here in your network, so actually let me do that in a different color to make it clear that this is not part of the network now. So, oh sorry, that didn't actually change my color. Yes. Doesn't seem to want to change my color. So let's go like that. So all of those lines there are weights. So we just compute the gradient with respect to those weights. And typically these days, as I mentioned, we use an auto differentiation package to do that. So you can basically construct these fairly complicated networks without having to worry about computing all of these gradients by hand. Instead, the software will do that for us. And turns out these gradients can always be computed if you're using differentiable functions, of course. These can always be computed in a compute that is comparable to the amount of compute it takes to do your forward pass. So if you can do that forward pass of this whole network in some limited amount of time, then computing the gradient will take time that is proportional to that. So it doesn't take much longer to compute the gradient. Okay, now that's in a nutshell deep learning. I want to say one more thing, which is if we then consider time step to time step, you could consider having a state here. This is our agent state now. And let's go a time step further to the next agent state. And these depend somehow on our observations. And maybe agent state is then used in some complicated way. And maybe they also result from the observations in some complicated way. And maybe these are used in some complicated way to maybe get our value and maybe to get our policy. And maybe other things as well. Now, this step, this agent update function, could be considered, let me actually put it somewhere else. Let me put that here. Because the agent update function, in some sense, merges that arrow and this part. So it merges the observation and the previous state into a new state. That's the definition of the agent update function. And here we see how we could structure that in our implementations as a neural network. where there is now a gradient that might flow. Actually, let me use blue to denote the gradient flow. So if we want to update the prediction over here, the gradient might flow into the parameters here, into the parameters looking at the observation, and also maybe through time, maybe even further back. So there could have been, then you use prime S to denote the previous one, and the gradient could flow all the way back through time. Now this is both nice and potentially beneficial, but it's also potentially problematic, because that means that if you want to actually have the gradient flowing all the way through time, you need to do something smart about how that gradient flows. That's beyond the scope of this course. That's more for more advanced deep learning considerations. There are mechanisms that allow you to do that, for instance by just truncating the gradient flow at some time step in the past and saying, well, I'm just going to do it a couple of steps. That's called backpropagation through time. Backpropagation in general is just a term refers to computing all of those gradients going backwards through these nonlinear structures. Okay, so that's just a brief, very brief explanation of deep learning. Some of that might be completely known to you already if you previously took a deep learning course. Here I just wanted to highlight that this is one way to build these structures and that you can then use them to basically compute your value functions. I want to mention yet one more little thing, which is kind of the same as what I said before, which is what convnets are. So this structure that we've seen before, actually let me highlight that again, is a nonlinear network. Now I'm just going to say a special case of this is when you have vision inputs, which are structured, sometimes drawn like this, where these are kind of the pixels on the screen. So maybe you have some sort of a Pac-Man thing here, maybe trying to eat a ghost. So of course normally you'd see much more of the Pac-Man screen, but let's just do a simple example. Maybe there's a dot here that's eating as well. So these could be the pixels of the screen. And in fact, typically you could have multiple layers of these, because for instance, you could have an RGB input where one of these layers contains the red, one of them contains the green, and so on. And then what we can do is we can apply a linear layer to this. And then toss this through nonlinearity, exactly as before. But turns out if you just put all of those into, like you could take all of these pixels and just put them into some sort of a large flat vector, and then just do the thing that we did before. But that turns out that doesn't work that well, so we typically don't do that. So instead, what we typically do is we apply a special linear layer, which actually looks at a little patch, and then typically looks at that patch across the channels. So these are channels. So then it turns this little patch here that goes through the channels in a sense. It turns that into a vector and then applies a weight matrix to give us the next patch, which then gets turned into a spatial patch again. And potentially again, you could have multiple layers of those. And in fact, what we typically do is we don't actually turn it into a patch, we just turn it into a, so I'm actually going to backtrack that slightly. We just turn it into a number. So a little 1 pixel, and then having stacked layers of those. This is just a vector, but I'm stacking it. And then we're going to compose those again into some larger image. The number of layers here, the number of channels here, does not have to match with the previous one. So we could have more channels here, and the semi-image in some sense could be smaller. This is called a convnet, and then what happens in a convnet is that actually the same weights get applied to different patches. So also over here. That's called weight sharing in general, and convnets use weight sharing. So essentially what's happening here is you could consider this to be kind of a filter, and this filter gets moved across the image, and basically on every patch in the image it gets applied the same filter, and it extracts some feature information which passes it into a new feature layer.
And then we get something that sometimes is drawn a little bit like this, where, as mentioned, we could have multiple planes here, and then this goes into other planes, where these planes could have a different number. So let me just draw 3 this time. Or 4, let me just make it up as I go along. And this one patch here would show up as a single pixel in this new thing. But then there's an overlapping patch, for instance here, that would show up as the pixel just next to it. And so on and so on. And then we just can do the same thing again, and then there could be a new patch here that goes into a layer above there. So you could apply this multiple times. These are just, similar to before, these are just linear layers, and then we put nonlinearities basically just before computing this, this pixel over here. So this would still have this nonlinearity on top of this, because otherwise it's a linear network and everything kind of collapses to a linear function approximator. But nonlinear function approximation can be a richer class. So instead of necessarily being linear in the observations, this could now be nonlinear in your observation. And then you could apply this many, many times, and then eventually you could toss it into a vector and then maybe compute your value function on top of that. So that is all that a convnet is. It's exactly the same, except that the linear layer has some certain structure. So one way to consider that is that this matrix here at the beginning could be a conv layer, and that just means that that matrix has a very specific structure where the same weights show up in multiple places in the matrix. There's weight sharing. And in addition, there is some certain specific spatial structure where we're considering only these patches. Okay, so that's just a brief primer. There's much more to be said about this. This is kind of a poor explanation because we're only taking a little bit of time to talk about these aspects. So I just wanted to give you a flavor of it. If you don't fully understand that, there's loads of introductory material on deep learning on the in the wild. And there's courses on this. There's lots of stuff on the internet. So I encourage you, if you want to know more, please dig into that. If you first want to just continue with the rest of this course without fully understanding all of it, that's also perfectly okay. Okay, so then using these networks in reinforcement learning is called deep reinforcement learning. Fortunately, many of the ideas immediately transfer when using deep neural networks. We can do temporal difference learning, we can do Monte Carlo, we just replace the feature vector with a gradient in our updates. We can apply double learning if we need it, for instance, double DQN, double Q learning. We could use experience replay and all sorts of other intuitions and results. They do transfer. Some things don't. For instance, UCB is hard to transfer because UCB, I'm reminding you that this is an exploration method that we discussed in the second lecture, and it requires counts. So you need to know how often you've seen a certain state or state action pair if you want to do UCB. Turns out it's very hard to count with deep neural networks, or at least in the way that we need for UCB, because of generalization. So deep neural networks tend to generalize really well, and this makes them learn really quickly. And people are still trying to understand exactly the properties of these networks, because it also depends on which optimization mechanism you use. Because these days people typically don't use vanilla stochastic gradient descent, but they use gradient transformations on top of that. Now, if you whether you do that or not, it turns out it's just very hard to count with these neural networks in terms of the states in reinforcement learning, and therefore it's hard to apply some sort of a bound like UCB does. Although people have considered extensions that do seem to maybe be somewhat reasonable, but it's still active research. Also, least squares methods don't really transfer that well because they're specifically made for the linear case, and then you can analytically compute these solutions. But in the generic case for nonlinear functions, it's really hard to compute those solutions because there's nonlinearities involved. That means that we can't just immediately write down what the optimal weight vector is for a specific data set to fit it. And instead, what people typically do is just use gradient methods to incrementally find them. So instead of doing these squares, people do experience replay. So let me now walk you through an example where an online neural Q-learning agent that combines these approach might include a neural network, which takes your observations and outputs, say, an action out Q value. So the idea is that this is just some nonlinear function that just looks at the pixels of the screen, let's say of Pac-Man, and then has some maybe conv layers to first do the spatial reasoning, then merges that into a vector, then maybe has a couple of other layers, And then at the end, it outputs the same number of elements as you have actions. And then we just index that with the action that we're interested in if we want a specific action value. Now note that I have ignored agent state here. So the agent state is basically just your observation in this case. So this wouldn't have memory. And maybe that's okay for some games like Pac-Man. Then we need an exploratory policies. For instance, you could just do epsilon greedy on top of this weight vector that we have. So that our action that we actually select will be greedy with respect to these action values with probability 1 minus epsilon and fully random with probability epsilon. And then we have a weight update to the parameters of this network where we use, in this case, gradient Q-learning, which you might recall the Q-learning update. Let me just briefly mention it again. It's going to be your immediate reward plus the discounted value of the maximum value action in the next state minus our current estimate times the gradient of that current estimate. That will be a gradient extension of Q-learning. I did mention a couple of downsides like overestimation. You could plug in solutions here as well. This is just for giving you a simple example. Then we could use an optimizer. So typically what people do is they take this update according to STD, this gradient in some sense. It's a semi-gradient actually because of the weights also being here but being ignored. But people take this and then they transform it. For instance, applying momentum so that you take a little bit of the previous update and you merge that in, or using more fancy optimizers like RMS prop and the Atom optimizer. Those are quite popular these days. And then turns out this often works better when using deep neural networks. Details are not too important for us right now. Often when I said we were using these auto differentiation packages often these days, so what people quite often do, what you'll see in code quite often, is they implement this weight update via a loss, but it's a little bit of a weird thing. So I'm mentioning this because it makes it easier to understand, for instance, other people's code. But in some sense, it's a little bit of a strange thing because there's this really strange operator here, which is called a stop gradient in most software frameworks. So basically what people do then is they say, oh, let's just write it down as if it's a loss, but let's ignore the gradient flowing into this part. And then if you take the gradient of this thing, but you ignore the gradient going into this part, you get that update that we had above. This kind of makes it explicit that this is not a real gradient algorithm, right? We actually have to manually specify, oh yeah, take the gradient, but don't push the gradient into that part. And if you do push the gradient into that part, you're doing one of these Bellman residual minimization algorithms instead. And as I mentioned, that tends to work slightly worse in practice. So you could play with this, you could try that out and see if the same holds for you, that works worse. And then people implement this as a loss so they can say, oh, just minimize that. Just apply stochastic gradient descent on that. Alternatively, of course, what you could also do is you could just compute this temporal difference error, this Q-learning temporal difference error here, and just compute the gradient with respect to the action values. Then you don't need that stop gradient operation, and then you could also implement it like that. What we're basically doing in some sense there is akin to doing one step of the chain rule by hand, the very simple first step of the chain rule by hand, to construct the update directly instead of first formulating it as some sort of a loss. It's not a real loss. It's not because of the stop gradient. So I'm hesitant to call that a real loss, although people do call these things real losses, even if people call these things losses, even if they're stop gradients. I'm just hesitant to do that because we're not actually following the gradient with respect to the parameters if there are stop gradients involved. So this just happens to have the right gradient if you compute this with an auto differentiation package. That's just for awareness, essentially, if you want to implement this. And now we can finally move to the DQN algorithm. So I showed examples of this all the way at the beginning of the course where we saw this agent playing Atari games, and now we finally accumulated enough knowledge that we could actually replicate that. So I'm going to explain what is in that algorithm, and it's very similar to what we saw just now. So there's a neural network, exactly as I said just now. The observation here is a little bit special. So the observation in DQN is not just the pixels on the screen. It's actually taking a couple of frames, a couple of steps into the past, and also doing some operations on that. So the original DQN algorithm would downscale the screen slightly for computational reasons. It would grayscale it, so instead of keeping the color information. This actually throws away a little bit of information. So in recent approaches, people sometimes don't do that anymore. And in addition to that, it would stack a couple of frames, so that it has some slight history, and there were two reasons for that. One is, for instance, in a game like Pong, where you're hitting a ball from one pedal to the other, it was thought that maybe this is important to be able to capture the direction of the ball. Because if you just know where the ball is, then you don't necessarily know whether it's going left or right. In the game of Pong, that might not actually be that consequential. That might not be necessary to know that for picking the right action. But in other games, you could imagine that sometimes that information is quite useful. But there's a different reason as well, which is that in the Atari games, in the simulator at least, and maybe in the original games as well, I don't actually know, the screen would sometimes flicker. So certain enemies might sometimes be there on one frame, but they wouldn't be there on the next frame. So therefore, that was important to consider a couple of frames rather than just one frame, because the network otherwise doesn't actually have any memory. So a different way to say that is that actually the input here are not the raw observations, but there's just a very simple handcrafted agent update function, which looks at the observations, which could be considered the raw frames, and then stacks them and processes them appropriately to give you an agent state, but there's still no long-term memory. Of course, there's a need for an exploration policy, and indeed in DQN this was literally taken to be epsilon greedy with a small epsilon like 0.05 or 0.01. And there was a replay buffer where you could store and sample past transitions. This replay buffer didn't store all of the transitions, instead it stored like the last 1 million transitions or something like that. So at the time when you go beyond 1 million transitions, then it would start throwing them away. And in addition, there's this subtle other thing, which was called a target network. And this was one of the innovations that made DQN work more effectively. So we're going to define a new weight vector that contains all of the weights of a network of exactly the same shape and size as the neural network that defines our Q value. And we're going to use that to bootstrap. So the weight update function is exactly the same as the online Q-learning algorithm that we saw on the previous slide, except for this one change where there's a W minus here. W minus is just a name. The minus doesn't mean it's negative or anything. It's just a name to say, oh, this is a different weight vector, different from the one that we're updating W. So then if we're not updating W minus, how does that one update? Well, that one is just updated by copying in occasionally the online weight vectors. So what this means is that during learning, you're basically regressing on a different value function for a while keeping it fixed for say 10,000 steps, and then you copy in the online weight so that occasionally it does get better over time. This makes the learning target a little bit more stable, and it was helpful for learning in DQN. This might sound a little bit similar and familiar when we talked about double learning for double Q learning. This is not quite double Q learning yet, because it is still using the same parameters here to evaluate the action and to pick the action. It's just using this W minus. Now, maybe something for you to think about. Oh, how would you then implement double learning in this framework? What would that look like? And then there was an optimizer applied to actually minimize the loss. In the original DQN, this was RMS prop. So this update would be tossed into the RMS prop optimizer, which also stores some statistics of past gradients, and then would compute the actual updates by taking all of that into account. Current day, people still use RMS prop or Atom typically, or variations of this. The replay and the target networks are designed to make the reinforcement learning look a little bit more like supervised learning, and the reasoning behind that was essentially that if you make it look more like supervised learning, it's more likely to work, because we already know that deep learning works quite well for supervised learning, for regression and classification for supervised data sets. The replay kind of scrambles the data so that the sampling seems more IID than if you would just give all of the samples sequentially. And the target network just makes the regression target less non-stationary on every single time step. And this might help the learning dynamics. Neither of those is strictly necessary for good learning, but in the DQN setup they did help performance, and they are still sometimes used in modern algorithms as well, and sometimes to much effect. Okay, so that brings us basically to the end of this lecture, where these last two things are kind of an intriguing like insight into what makes deep reinforcement learning an interesting field. So turning the replay and the target networks, making use of that to make the reinforcement learning look more like supervised learning. This was done, of course, because we're combining the deep learning part in. So in some sense, you could say this is deep learning aware reinforcement learning. So we're changing the reinforcement learning update a little bit with these target networks And we're using experience replay deliberately here because this makes better use then of these deep networks that we're using. The converse also exists. There are also things that could be called reinforcement learning aware deep learning, where sometimes people change, for instance, the network architecture or the optimizer in certain ways to maybe play better with the fact that we're doing reinforcement learning. The fact that these exist, that there are some important design considerations that could be called deep learning aware reinforcement learning or reinforcement learning aware deep learning. This is exactly what makes deep reinforcement learning a field of its own in some sense, a subfield of its own, with really interesting research questions that are not pure reinforcement learning questions, they're not pure deep learning questions, but they're really on this intersection of these two really exciting fields. Okay, that brings us to the end of this lecture. As always, please ask questions on Moodle if you have any, and in our live Q&A. Thanks for your attention.